This comprehensive
Seems like my KCB, our electricity supplier here, doesn't want me to continue my streams. Anyhow, power loss happened here, so that's why my earlier stream ended abruptly. Let me just position my camera here. It's a bit slanted. Anyhow, without yeah, let me just continue with my tutorial. So let me just go to the segment. We were at introduction.
Hello and welcome back. With first the input to read. We've spent a bunch of time in the Pytorch documentation tree. We're in computer vision. My problem is,
That's my.
and then in here, you can write some code. Be sure to format it as best you can. That way it'll help us answer it. And then go, what's happening here? Now, why do I format the code in these backticks here? It's so that it looks like code and that it's easier to read when it's formatted on the GitHub discussion. Then you can select a category. If you have a general chat, an idea, a poll, a Q&A, or a show and tell of something you've made or for what you've learned from the course. For question and answering, you'll want to put it as Q&A. Then you can click Start Discussion, and it'll appear here, and that way they'll be searchable, and we'll be able to help you out. So I'm going to get out of this. And speaking of resources, we've got the Pytorch Deep Learning repo. The links will be where you need the links. All of the code that we're going to go through. Let's get steak with my dad. Extra hours in 1 minute and 30. I'm going to play it all. Use standard to send in to turn it. For example, just play it to play. But what are we going to? We're going to get a vision data. Well, we're machine like the. So in the last video we covered what we're going to.
All right. I think this is the part
we saw
where
some
we left
examples
off.
of what computer vision problems are.
Continue.
Essentially, anything that you're able to see, you can potentially turn into a computer vision problem. And we're going to be cooking up lots of machine learning, or specifically Pytorch computer vision code. You see I fixed that typo. Now let's talk about what the inputs and outputs are of a typical computer vision problem. So let's start with a multi-class.
I think we need to skip just a bit.
So red, green, and
Yeah,
blue.
this should be
so
perfect.
If we look at this up, if we go red, green, blue image format. So 24-bit RGB images. So a lot of images or digital images have some value for a red pixel, a green pixel, and a blue pixel. And if you were to convert images into numbers, they get represented by some value of red, some value of green, and some value of blue. That is exactly the same as how we'd represent these images. So for example, this pixel here might be a little bit more red, a little less blue, and a little less green because it's close to orange. And then we convert that into numbers. So what we're trying to do here is essentially what we're trying to do with all of the data that we have with machine learning is represent it as numbers. So the typical image format to represent an image, because we're using computer vision, so we're trying to figure out what's in an image. The typical way to represent that is in a tensor that has a value for the height, width, and color channels. And so we might
I haven't set the playback speed to 2x. That's why Daniel was. I felt Daniel was speaking slower than usual.
numerically encode these. In other words, represent our images as a tensor. And this would be the inputs to our machine learning algorithm. And in many cases, depending on what problem you're working on, an existing algorithm already exists for many of the most popular computer vision problems. And if it doesn't, you can build one. And then you might fashion this machine learning algorithm to output the exact shapes that you want. In our case, we want 3 outputs. We want 1 output for each class that we have. We want a prediction probability for sushi. We want a prediction probability for steak. And we want a prediction probability for pizza. Now, in our case, in this iteration, looks like our model got one of them wrong because the highest value was assigned to the wrong class here. So for the second image, it assigned a prediction probability of 0.81 for sushi. Now, keep in mind that you could change these classes to whatever your particular problem is. I'm just simplifying this and making it 3. You could have 100, you could have 1,000, you could have 5. It's just, it depends on what you're working with. And so we might use these predicted outputs to enhance our app. So if someone wants to take a photo of their plate of sushi, our app might say, hey, this is a photo of sushi. Here's some information about the sushi rolls. Or the same for steak, the same for pizza. Now, it might not always get it right, because after all, that's what machine learning is. It's probabilistic. So how would we improve these results here? Well, we could show our model more and more images of sushi, steak, and pizza so that it builds up a better internal representation of said images. So when it looks at images it's never seen before, or images outside its training data set, it's able to get better results. But just keep in mind, this whole process is similar no matter what computer vision problem you're working with. You need a way to numerically encode your information. You need a machine learning model that's capable of fitting the data in the way that you would like it to be fit. In our case, classification. You might have a different type of model if you're working with object detection, a different type of model if you're working with segmentation. And then you need to fashion the outputs in a way that best suit your problem as well. So let's push forward. Oh, by the way, the model that often does this is a convolutional neural network. In other words, a CNN. However, you can use many other different types of machine learning algorithms here. It's just that convolutional neural networks typically perform the best with image data. Although, with recent research, there is the transformer architecture, or deep learning model, that also performs fairly well, or very well, with image data. So just keep that in mind going forward. But for now, we're going to focus on convolutional neural networks. And so we might have input and output shapes, because remember, one of the chief machine learning problems is making sure that your tensor shapes line up with each other, the input and output shapes. So if we encoded this image of steak here, we might have a dimensionality of batch size, width, height, color channels. And now the ordering here could be improved. It's usually height, then width, so alphabetical order, and then color channels last. So we might have
I guess batch size is like how many, uh, like even though there are three RGB channels, how many, like that image, how many like each individual. If the image was a cake is a loaf of bread. I think that's way to put it. How many like batches do you want to cut it into? I guess that's
shape
what
of
batch
none, 2 to 4,
size
2 to 4,
is.
3. Now, where does this come from? So none could be the batch size. Now, it's none because we can set the batch size to whatever we want, say, for example, 32. Then we might have a height of 2 to 4 and a width of 2 to 4 and 3 color channels. Now, height and width are also customizable. You might change this to be 512 by 512. What that would mean is that you have more numbers representing your image, and in sense would take more computation to figure out the patterns because there is simply more information encoded in your image. But 224 is a common starting point for images. And then 32 is also a very common batch size, as we've seen in previous videos. But again, this could be changed depending on the hardware you're using, depending on the model you're using. You might have a batch size of 64, you might have a batch size of 512. It's all problem specific. And that's this line here. These will vary depending on the problem you're working on. So in our case, our output shape is 3 because we have 3 different classes for now. But again, if you have 100, you might have an output shape of 100. If you have 1,000, you might have an output shape of 1,000. The same premise of this whole pattern remains though. Numerically encode your data, feed it into a model, and then make sure the output shape fits your specific problem. And so, for this section, computer vision with Pytorch, we're going to be building CNNs to do this part. We're actually going to do all of the parts here, but we're going to focus on building a convolutional neural network to try and find patterns in data, because it's not always guaranteed that it will. Finally, let's look at one more problem. Say you had grayscale images of fashion items, and you have quite small images, they're only 28 by 28. The exact same pattern is going to happen. You numerically represent it, use it as inputs to a machine learning algorithm, and then hopefully your machine learning algorithm outputs the right type of clothing that it is. In this case, it's a t-shirt. But I've got dot here because we're going to be working on a problem that uses 10 different types of items of clothing. And the images are grayscale, so there's not much detail. So hopefully our machine learning algorithm can recognize what's going on in these images. There might be a boot, there might be a shirt, there might be pants, there might be a dress, etc., etc. But we numerically encode our images into dimensionality of batch size, height, width, color channels. This is known as NHWC, or number of batches, or number of images in a batch, height, width, C, or color channels. This is color channels last. Why am I showing you two forms of this? Do you notice color channels in this one is color channels first, so color channels height, width? Well, because you come across a lot of different representations of data full stop, but particularly image data in Pytorch and other libraries, many libraries expect color channels last. However, Pytorch currently, at the time of recording this video, it may change in the future, defaults to representing image data with color channels first. Now this is very important because you'll get errors if your dimensionality is in the wrong order. And so there are ways to go in between these two, and there's a lot of debate of which format is the best. It looks like color channels last is going to win over the long term, just because it's more efficient, but again, that's outside the scope. But just keep this in mind. We're going to write code to interact between these two, but
All
it's the same
right.
data, just represented in different order. And so we could rearrange these shapes to how we want, color channels last or color channels first. And once again, the shapes will vary depending on the problem that you're working on. So with that being said, we've covered the input and output shapes. How are we going to see them with code? Well, of course, we're going to be following the Pytorch workflow that we've done. So we need to get our data ready, turn it into tensors in some way, shape, or form. We can do that with torque division transforms. Oh, we haven't seen that one yet, but we will. We can use
Oops, hold on a second. I haven't plugged my laptop in. Oh, I have plugged my laptop in, but it isn't charging for some reason. Give me a second.
torque utils data.dataset, utils.data.
There we go. I hadn't plugged the actual. Like I turned on my laptop charger, but I did not plug it. Happens to the best of us, huh?
We've got a whole bunch of modules to help us with that. Torch module, torch vision.models. And then we have an optimizer and a loss function. We can evaluate the model using torch metrics, or we can code our own metric functions. We can, of course, improve through experimentation, which we will see later on, which we've actually done that, right? We've done improvement through experimentation. We've tried different models, we've tried different things. And then finally, we can save and reload our trained model if we wanted to use it elsewhere. So with that being said, we covered the workflow. This is just a high-level overview of what we're going to code. You might be asking the question, what is a convolutional neural network, or a CNN? Let's answer that in the next video. I'll see you there. Welcome back. In the last video, we saw examples of computer vision input and output shapes. And we kind of hinted at the fact that convolutional neural networks are deep learning models, or CNNs, that are quite good at recognizing patterns in images. So we left off last video with the question, what is a convolutional neural network? And where could you find out about that? What is a
Well, it's search for it first before looking into the tutorial. It's a CNN model. Uh, convolutional neural network. I am pretty sure I'm pronouncing that wrong. Is a network architecture for deep learning that learns directly from data. Hmm. CNNs are particularly useful for finding patterns in images to recognize objects, classes, and categories. They can also be quite effective for classifying audio, time series, and signal data. Basically, what I'm gonna take away from this is if you have data, you need to use CNN as such, particularly image data. All right, let's
Convolutional
continue.
neural network. Here's one way to find out. And I'm sure, as you've seen, there's a lot of resources for such things. A comprehensive guide to convolutional neural networks. Which one of these is the best? Well, it doesn't really matter. The best one is the one that you understand the best. So there we go. There's a great video from Code Basics. I've seen that one before. Simple explanation of convolutional neural network. I'll leave you to research these things on your own. And if you wanted to look at images, there's a whole bunch of images. I prefer to learn things by writing code because remember, this course is code first. As a machine learning engineer, 99% of my time is spent writing code. So that's what we're going to focus on. But anyway, here's the typical architecture of a CNN. In other words, a convolutional neural network. If you hear me say CNN, I'm not talking about the news website. In this course, I'm talking about the architecture of convolutional neural network. So this is some Pytorch code that we're going to be working towards.
That's what
We have some
like when I heard CNN first. That's the image which came into my mind. Isn't that a? I was like, isn't that a news channel? That's what it was.
We have an input layer.
Yeah.
So we have an input layer which takes some in channels and an input shape. Because remember, it's very important in machine learning and deep learning to line up your input and output shapes of whatever model you're using, whatever problem you're working with. Then we have some sort of convolutional layer. Now, what might happen in a convolutional layer? Well, as you might have guessed, as what happens in many neural networks, is that the layers perform some sort of mathematical operation. Now, convolutional layers perform convolving window operation across an image or across a tensor and discover patterns using, let's have a look actually. Let's go nn.com2d. There we go. This is what happens. So the output of our network equals a bias plus the sum of the weight tensor over the convolutional channel out, okay, times input. Now, if you want to dig deeper into what is actually going on here, you're more than welcome to do that. But we're going to be writing code that leverages the torch nn.com2d, and we're going to fix up all of these hyperparameters here so that it works with our.
Again, we will go further into the math after we finish this and that tutorial.
What you need to know here is that
I'm very sure that we need to have a very good understanding of it if we really want to become good at
we'll see things later on
machine
with code.
learning.
So just keep that in mind. This is what's happening. As with every layer in a neural network, some form of operation is happening on our input data, and those operations happen layer by layer until eventually, hopefully, they can be turned into some usable output. So let's jump back in here. Then we have hidden activation / nonlinear activation because why do we use nonlinear activations? Well, it's because if our data was nonlinear, non-straight lines, we need the help of straight and non-straight lines to model it, to draw patterns in it. Then we typically have a pooling layer. And I want you to take this architecture, I've said typical here for a reason, because these type of architectures are changing all the time. So this is just one typical example of a CNN. It's about as basic as a CNN as you can get. So over time, you'll start to learn to build more complex models. You will not only start to learn to build them, you will just start to learn to use them, as we'll see later on in the transfer learning section of the course. And then we have an output layer. So do you notice the trend here? We have an input layer, and then we have multiple hidden layers that perform some sort of mathematical operation on our data. And then we have an output / linear layer that converts our output into the ideal shape that we'd like. So we have an output shape here. And then how does this look in process? Well, we put in some images. They go through all of these layers here because we've used nn.sequential. And then hopefully this forward method returns x in a usable status or usable state that we can convert into class names. And then we could integrate this into our computer vision app in some way, shape, or form. And here's the asterisk here. Note, there are almost an unlimited amount of ways you could stack together a convolutional neural network. This slide only demonstrates one. So just keep that in mind. Only demonstrates one. But the best way to practice this sort of stuff is not to stare at a page. It's to, if in doubt, code it out. So let's code. I'll see you in Google Colab. Welcome back. Now, we've discussed a bunch of fundamentals about computer vision problems and convolutional neural networks.
Open up
let's start to code them out. I'm
going to be new notebook on this side.
Just going to clean up some of these tabs. And I'm going to start a new notebook. And then I'm going to name this one,
Same
it's going to be Pytorch Computer Vision. And I'm going to call mine video. So just so it has the video tag. Because if we go in here, if we go video notebooks of the Pytorch deep learning repo, the video notebooks are stored in here. They've got the underscore video tag. So the video notebooks have all.
So we're not going to name it. Let's just
stick
to that.
So let me just write a heading here, Pytorch Computer Vision. And I'll put a resource here, see reference notebook. Now, of course, this is the one that's the ground truth. It's got all of the code that we're going to be writing. I'm going to put that in here. Explain with text and images and whatnot. And then finally is we've got C reference online book. And that is at learnpytorch.io at section number 3, Pytorch Computer Vision. I'm going to put that in there. And I'm going to turn this into Markdown with Command MM. Beautiful. So let's get started. I'm going to get rid of this, get rid of this. How do we start this off? Well, I believe there are some computer vision libraries that you should be aware of. Computer vision libraries in Pytorch. So this is going to be a text-based cell, but the first one is Torch Vision, which is the base domain library for Pytorch Computer Vision. So if we look up Torch Vision, what do we find? We have Torch Vision 0.12. That's the version that Torch Vision is currently up to at the time of recording this. So in here, this is very important to get familiar with if you're working on computer vision problems. And of course, in the documentation, this is just another tidbit. We have Torch Audio for audio problems. We have Torch Text for text. Torch Vision, which is what we're working on. Torch Rec for recommendation systems. Torch Data for dealing with different data pipelines. Torch Serve, which is for serving Pytorch models. And Pytorch on XLA, so I believe that stands for Accelerated Linear Algebra Devices. You don't have to worry about these ones for now. We're focused on Torch Vision. However, if you would like to learn more about a particular domain, this is where you would go to learn more. So there's a bunch of different stuff that's going on here. Transforming and augmenting images. So fundamentally, computer vision is dealing with things in the form of images. Even a video gets converted to an image. We have models and pre-trained weights. So as I referenced before, you can use an existing model that works on an existing computer vision problem for your own problem. We're going to cover that in section, I think it's 6 for transfer learning. And then we have datasets, which is a bunch of computer vision datasets, utils, operators, a whole bunch of stuff here. So Pytorch is really, really good for computer vision. I mean, look at all the stuff that's going on here. But that's enough talking about. Let's just put it in here. Torch Vision, this is the main one. I'm not going to link to all of these. All the links to these, by the way, is in the book version of the course, Pytorch Computer Vision. And we have what we're going to cover. Finally, computer vision libraries in Pytorch. Torch Vision, datasets, models, transforms, etc. But let's just write down the other ones. So we have Torch Vision, datasets, something to be aware of. So get datasets and data loading functions for computer vision here. Then we have Torch Vision. So these all come from Torch Vision. Models is get pre-trained computer vision. So when I say pre-trained computer vision models, we're going to cover this more in transfer learning, as I said. Pre-trained computer vision models are models that have been already trained on some existing vision data and have trained weights, trained patterns.
Hi, this was what he's writing is a markdown, isn't he? A markup? But
leverage for your own problems.
Yeah.
That you can leverage
I
for
think
your
it's
own
called
problems.
markdown.
Then we have Torch Vision transforms.
Just search that markdown. Yeah, it's called markdown, right? Anyhow.
And then we have functions for manipulating your vision data, which is of course images, to be suitable for use with an ML model. So remember, what do we have to do when we have image data or almost any kind of data for machine learning? We have to prepare it in a way, so it can't just be pure images. So that's what transforms help us out with. Transforms helps to turn our image data into numbers so we can use it with a machine learning model. And then of course we have these are the Torch utils. This is not vision specific, it's entirety of Pytorch specific, and that's dataset. So if we wanted to create our own dataset with our own custom data, we have the base dataset class for Pytorch. And then we have finally Torch utils data. These are just good to be aware of because you'll almost always use some form of dataset / data loader with whatever Pytorch problem you're working on. So this creates a Python iterable over a dataset. Wonderful. I think these are most of the libraries that we're going to be using in this section. Let's import some of them, hey, so we can see what's going on. Let's go import Pytorch. Import Pytorch. So import Torch. We're also going to get NN, which stands for neural network. What's in NN? Well, in NN, of course, we have lots of layers, lots of loss functions, a whole bunch of different stuff for building neural networks. We're going to also import Torch Vision. And then we're going to go from Torch Vision, import datasets, because we're going to be using datasets later on to get a dataset to work with. From Torch Vision, we'll import transforms. You can also go from Torch Vision, .transforms, import to tensor. This is one of the main ones you'll see for computer vision problems, to tensor. You can imagine what it does, but let's have a look. Transforms to tensor. Transforming and augmenting images. So look where we are. We're in pytorch.org/vision/stable/transforms over here. So we're in the Torch Vision section, and we're just looking at transforming and augmenting images. So transforming, what do we have? Transforms are common image transformations available in the transforms module. They can be trained together using compose. Beautiful. So if we have to tensor, what does this do? Convert a pill image or NumPy ND array to a tensor. Beautiful. That's what we want to do later on, isn't it? Well, this is going to be giving you a spoiler. Is we want to convert our images into tensors so that we can use those with our models. But there's a whole bunch of different transforms here, and actually, one of your extra curriculum is to read through each of these packages for 10 minutes. So that's about an hour of reading, but it will definitely help you later on if you get familiar with using the Pytorch documentation. After all, this course is just a momentum builder. We're going to write heaps of Pytorch code, but fundamentally, you'll be teaching yourself a lot of stuff by reading the documentation. Let's keep going with this. Where are we up to?
Hey, look at that. We have a second viewer on our channel right now. Hey to, whoever's watching my stream. Feel free to ask me any questions. Anyhow, let's continue here.
When we're getting familiar with our data, matplotlib is going to be fundamental for visualization. Remember, the Data Explorer's motto, visualize, visualize, visualize. Become one with the data. So we're going to import matplotlib.pyplot as PLT. And then finally, let's check the versions. So print torch.version, or __ version, and print Torch Vision. So by the time you watch this, there might be a newer version of each of these modules out. If there's any errors in the code, please let me know. But this is just a bare minimum version that you'll need to complete this section. I believe at the moment,
See what version. Let's compare the version that Daryl has and we have.
Google Colab is running 1.11 for Torch.
I made a typo there. To transforms. Nah. What did I do that? Oh, it should be Torch Vision. Hello, how's it going with the... Oh, we have a message from Checkham. How's it going with the Pytorch course, you ask? Really good. I mean, it's my 7th day with it, and so far it's been really, really well. Like, I've done quite a lot on machine learning. I would recommend this to anyone who wants to get into machine learning. The link is in my about section if you want to check it out. What's that badge you have there? Ah, uh-huh. You got that for watching Elden Ring when the DLC came out, huh? I play Elden Ring too. I guess you're into that.
Maybe, or maybe 1.10. We'll find out in a second. It just connected.
I was following that course too. I was like 4 to 5 hours in. Ah, okay. But you're in a web developer called you back, huh? So you couldn't finish it. Okay. Are you a web developer then, like an actual like working professional or a student? And I would recommend you to go back and finish it. It's really, really good. Like just imagine someone's out there giving you pure gold content for how many hours is this? 25 hours. A long time student, sadly. All right. Um, you should get into freelancing if you're looking for jobs and stuff.
So we're importing Pytorch.
I myself began my journey as a freelancer.
Okay, there we go. So my Pytorch version is 1.10, and it's got CUDA available, and Torch Vision is 0.11. So just make sure if you're running Google Colab.
Okay, now what? Uh, this should work. Oh, look at that. How many years ago was this process? So 1 year ago, all right.
If you're running this at a later date, you probably have.
We have a third viewer too. Hey there.
Versions, you might even have a later version. So these are the minimum versions required for this upcoming section. So we've covered the base computer vision libraries in PyTorch. We've got them ready to go. How about in the next video, we cover getting a data set. I'll see you there.
What exactly do you enjoy these days? Like, is it still web development or are you still trying to get into machine learning and stuff?
Welcome back. So in the last video, we covered some of the fundamental computer vision libraries in PyTorch. The main one being Torch Vision, and then modules that stem off Torch Vision. And then of course, we've got torchutils.data.dataset, which is the base dataset class for PyTorch, and data loader, which creates a Python iterable over a dataset. So let's begin where most machine learning projects do, and that is getting a dataset.
Wait, what? Dataset.
And data loader, which creates a Python iterable over a dataset. So
All
let's
right.
begin where most machine learning projects do, and that is getting a dataset. Getting a dataset. I'm going to turn this into Markdown, and the dataset that we're going to be used to demonstrating some computer vision techniques is fashion MNIST, which is a take. Well, the dataset we'll be using is fashion MNIST, which is a take on the original MNIST dataset, MNIST database, which is.
What is that? Let's do the research from our side. The MNIST database is a large database of. Oh, this is the. This looks pretty close to what was there on one black, one blue. I forgot the channel name. Black, blue, brown YouTube. Oh, three blue, one brown. Three blue, one brown. Neural network. Oh, okay. We have a message. I'll check it out. Yeah, this is the. I believe this is the same model he used here. What's it? 2 months ago, I did a break from code, but now it's time to come back to it. I was learning the MERN stack, but now I'll try to learn we're using Next.js. Uh, were you burned out? It happens to everyone. I myself, I believe I would, in the future get in depth into web development. Maybe I'll stream that. Yeah, I was burned out. Yeah, it happens to everyone. I myself was burned out a few months back, and I took literally I didn't code for like an entire month. Maybe not an entire month, but I took a very long break. Every now and so we should look back into our achievements like life is more than code, just code.
this Modified National Institute of Standards and Technology database, which is kind of like the hello world in machine learning and computer vision, which is these are sample images from the MNIST test dataset, which are grayscale images of handwritten digits. So this, I believe,
All right. Now, what is fashion MNIST then? Fashion MNIST data set. What do they have there? I was about to say dresses, and I guess I was right. All right, there we go. I guess we're gonna segregate these now. These
was originally
images.
used for trying to find out if you could use computer vision at a postal service to, I guess, recognize postcodes and whatnot. I may be wrong about that, but that's what I know. Yeah, 1998. So all the way back at 1998. How cool is that? So this was basically where convolutional neural networks were founded. I'll let you read up on the history of that. But neural networks started to get so good that this data set was quite easy for them to do really well. And that's when Fashion MNIST came out. So this is a little bit harder. If we go into here, this is by Zalando Research, Fashion MNIST, and it's of grayscale images of pieces of clothing. So like we saw before, the input and output, what we're going to be trying to do is turning these images of clothing into numbers and then training a computer vision model to recognize what
Oh wait, that's really cool. We need to check it out. He went to the GitHub page, didn't he? Is this? I thought it was mouse control. Seems like it's just video, but it that looks really cool. I wonder what that is. So, like, what is this representation? MNIST is often the first dataset researchers try. If it doesn't work on MNIST, it won't work at all. Well, if it does work on MNIST, it may still fail on others. Okay. MNIST is too easy. I guess yeah, because it's just digits on there. This is more complicated. Yeah, I agree. MNIST is overused. I don't know about that. I'm not that. I'm just new to machine learning and stuff. Yeah, not new, but anyway, MNIST cannot represent modern CV tasks. T-shirt. Okay, it seems like they have 10, 10 labels. They have a T-shirt, trouser, pullover, dress, coat, sandals, shirt, sneaker, bag, ankle boot. I don't know why why I'm just iterating what's written here. Obviously, guys can see it. And yeah, loading data. Okay, let's get back to tutorial.
And here's a dimensionality plot of all the different items of clothing, visualizing where similar items are grouped together. There's the shoes and whatnot. Is this interactive? Oh no, it's a video. Excuse me. There we go. To serious machine learning researchers. We're talking about replacing MNIST. MNIST is too easy. MNIST is overused. MNIST cannot represent
Seems like now Daniel is just gonna echo what is over
modern
there.
CV tasks. So even now, Fashion MNIST, I would say, has also been pretty much solved, but it's a good way to get started. Now, where can we find such a data set? We could download it from GitHub, but if we come back to the Torch Vision documentation, have a look at datasets, we have a whole bunch of built-in datasets. And remember, this is your extracurricular to read through these for 10 minutes or so each.
Did you try the Hugging Face machine learning course too, or this is the first one that I'm doing? Um, I'm not sure which Hugging Face course you are referring to. If you can send the link, I'll check it out. But I have used Hugging Face in a way, just their plain inference models, and I've also kind of deployed. I don't know what they call it. Is deployment. They have a specific name for it, don't they? Solutions, yeah. Solutions pricing. Yeah, inference endpoints. I have deployed a couple of inference endpoints and everything, but that's as far as I got with Hugging Face. If you can put down the link in chat, I'll check it out. I'm not sure which course you're referring to, but yeah, I have used Hugging Face in some of my projects that I already built.
But we have an example. We could download ImageNet if we want. We also,
You know what's happening here?
but this is your extracurricular to read through these for 10 minutes or so each. But we have an example. We could download ImageNet if we want.
All the research as a class.
We also have some base classes here for custom datasets. We'll see that later on. But if we scroll through, we have image classification datasets.
Is it?
Caltech 101. I don't even know what all these are. There's a lot here. CFAR 100. So that's an
Is in
example.
Caltech University. I know that from the what's it? the series where Shell, yeah, Big Bang Theory, yeah. I mean, you know about these courses as well. Yeah. Oh, you were asking me, have I checked into any Hugging Face machine learning course? I guess that's what your question was. I haven't looked into any course as such, but at that point, I just want to start with machine learning as soon as possible. So I did Hugging Face. I'll just show you the video. Hugging Face, inference endpoint. See, this is what I use for. Why is it? Anyhow, let's see. There was this person over here. Hugging Face, inference. Hmm. Not Pytorch, Python. Yeah, there we go. It was this guy over here. Hugging Face getting. This is just this is the only video I've checked out on Hugging Face. Just to get started, I just want to get a quick understanding of what transformers were and how do I use it. Pipeline tokenize, and so basically how to use that inference endpoint is what I want to know. You know what? I'll drop this in chat, so if you want to check it out, you can. Let me do that. That. There you go. That. There you go. That. There you go. Okay, it's weird seeing myself on stream. Yeah.
Different items. So that would be a 100 class multi-class classification problem. C510 is 10 classes. We have EM-NIST. We have fashion.
Would you look at that? You're welcome. You're welcome. You're more than welcome. Our counter,
and then you would turn it into
our viewer counter is also increasing now.
So ImageNet is one of the most popular, or is probably the gold standard dataset for computer vision evaluation.
Oh, that's another database. Let's check that out first. ImageNet. It's an image database according to the WordNet hierarchy. The data is available for free. All right, let's do they have pictures of what the data is exactly? Maybe we'll see it in the tutorial itself.
It's quite a big dataset. It's got millions of images, but that's the beauty of Torch Vision is that it allows us to download example datasets that we can practice on, or even perform research on from a built-in module. So let's now have a look at the fashion MNIST data.
There is also the Harvard course about AI if you haven't heard of it. I haven't heard of a Harvard gosh, I can't pronounce about a Harvard course on AI. But I do I do know about the famous, what do they call it, CS50 or something, like every time you want to get into coding as such, that's the recommended course which pops up. Let's see what you meant. Oh,
this core
Harvard CS50s. Oh, they do an AI course too. I thought they only did like a common introduction and stuff. I believe this would be more into the math side of it and all, right? But about web development. Yeah, of course, yeah. Although in the initial course, I think they just cover the basics of Python and I believe. Anyhow, yeah. This is I would believe this would be more of rather than a hands-on training. It would be more of a theoretical video, right? Actually, check that out. Yeah. Um. Yeah. Anyway, my aim, once I complete this course from Pytorch is to get into more of the math side of things. Right now, I'm just using the algorithms as they are, with just a basic understanding of the math involved. You're probably right, actually. Hmm. Right on which part? Sorry. Um.
Dataset. How might we get this? So we've got some example code here, or this is the documentation, torchvision.datasets.fashionmnest. We have to pass in a root, so
Oh, so this. But this is all is already on Torch
where we
Vision
want to
now.
download the dataset. We also have to pass in whether we want the training version of the dataset or whether we want the testing version of the
In our case, we just. Yeah. It's right. I mean, I agree with you. Like, to get into machine learning, you don't really need to or maybe I'm wrong there because I'm relatively new to this field, but I really believe that if you want to become an expert in machine learning, there's no way around it. You need to understand the math involved. But to begin, like if you just begin with the math, you'll get overwhelmed and won't start with it. So get into the coding side of it first, and later on, do the math side of it is my plan, anyways. And you can follow it if you want to, or at least I. Nah, I mean, that's what Pytorch is helpful for, and it covers a lot of math for us. Although understanding that math is equally important, I would say.
dataset.
Gosh, it is a bit on the brighter side. It's a sunny day.
We want to download it, yes or no? Should we transform the data in any way, shape, or form? So we're going to be downloading images through this function call or this class call. Do we want to transform those images in some way? What do we have to do to images before we can use them with a model? We have to turn them into a tensor, so we might look into that in a moment. And target transform is, do we want to transform the labels in any way, shape, or form? So often the datasets that you download from torchvision.datasets are pre-formatted in a way that they can be quite easily used with Pytorch, but that won't always be the case with your own custom datasets. However, what we're about to cover is just important to get an idea of what the computer vision workflow is, and then later on you can start to customize
Yeah.
how you get your data in the right format to be used with the model. Then we have some different parameters here and whatnot. Let's just, rather than look at the documentation, if in doubt, code it out. So we'll be using fashion mnest.
If in doubt, got it out.
And we'll start by, I'm going to just put this here, from torchvision.datasets. And we'll put the link there. And we'll start by getting the training data. Set up training data. I'm trying to make some code cells here so that I can code in the middle of the screen. Set up training data. Train data equals datasets.fashionmnest. Because recall, we've already, from Torch Vision,
Have I imported? Maybe I've imported datasets.
we don't need to import this again. I'm just doing it for demonstration purposes. But from Torch Vision, import datasets. So we can just call datasets.fashionmnest. And then we're going to type in root. See how the doc string comes up and tells us what's going on. I personally find this a bit hard to read in Google Colab. So if I'm looking up the documentation, I like to just go into here. But let's code it out. So root is going to be data. So where to download data to. We'll see what this does in a minute. Then we're going to go train. We want the training version of the dataset. So as I said, a lot of the datasets that you find in Torch
Try to download the data too. Okay. But we don't have a folder, do we? We don't have a data folder. Maybe it creates one automatically for us if it doesn't exist. What is train?
vision.datasets have been formatted into training dataset and testing dataset already. So this boolean tells us, do we want the training dataset? So if that was false, we would get the testing dataset of FashionMNest.
Okay,
do we want to download it? Do we want to download? Yes, no. So yes, we do. We're going to set that to true. Now, what sort of transform do we want to do? So because we're going to be downloading images, and what do we have to do to our images to use them with a machine learning model? We have to convert them into tensors. So I'm going to pass the transform to tensor, but we could also just go torchvision.transforms.toTensor. That would be the exact same thing as what we just
Alright, so it just transforms this to tensors for us automatically.
the transform to tensor, but we could also just go torchvision.transforms.toTensor. That would be the exact same thing as what we just did before. And then the target transform, do we want to transform the labels? No, we don't. We're going to see how they come, or the targets, sorry. Pytorch is another way, another naming convention, often uses target for the target that you're trying to predict, so using data to predict.
What is target transform?
To tensor. That would be the exact same thing as what we just did before. And then the target transform, do we want to transform the labels? No, we don't.
Do we want to transform the outputs? Okay.
We're going to see how they come, or the target, sorry. Pytorch is another way, another naming convention, often uses target for the target that you're trying to predict, so using data to predict the target, which is I often use data to predict a label. They're the same thing. So how do we want to transform the data? And how do we want to transform the labels slash targets? And then we're going to do the same for the test data. So we're going to go datasets. You might know what to do here. It's going to be the exact same code as above, except we're going to change one line. We want to store it in data.
Well, then let's
We
just
want to
copy
download the
it.
training dataset as false because we want the testing version. Do we want to download it? Yes, we do. Do we want to transform it, the data? Yes, we do. We want to use toTensor to convert our image data to tensors. And do we want to do a target transform? Well, no, we don't. We want to keep the label slash the targets as they are. Let's see what happens when we run this. Downloading fashion MNest. Beautiful. So this is going to download all the labels where we have train images.
Alright, let's run this, and of course we had to get an error. Okay, I made a typo there, didn't I? It's not transform, it's transform and transform. There we go. Why do I keep on making these typos? Let's see. Yep, that should do it. Well, Daniel's got block ran way faster than us for some reason. Anyhow,
Train labels, lovely. Test images, test labels, beautiful. So that's how quickly we can get a data set by using Torch Vision datasets. Now, if we have a look over here,
maybe it might have something to do with him using
have a
the
data folder,
paid
so we set the
version.
root to be data. Now, if we look what's inside
Yeah,
here,
it's not that
exactly what we
slow.
wanted. Then we have the raw, and then we have a whole bunch of files here, which Torch Vision has converted into datasets for us. So let's get out of that. And this
Let's look at our train data and test data. I would assume they're tensors. So let's just look at the first 10 values. Only one element tensors can be converted to Python scalars. Let's just look at what they are first. Then.
process would be much the same.
They're,
Used almost any dataset in here. Of course,
let's just print out the type. I'm pretty sure they're just in a fast format of some sort, perhaps.
they might be slightly different depending on what the documentation says and depending on what the dataset is, but that is how easy Torch Vision.datasets makes it to practice on example computer vision datasets. So let's go back. Let's check out some parameters or some attributes of our data. How many samples do we have? So we'll check the lengths.
So we have 60,000 and 10,000 emissions respectively.
We have 60,000 training examples and 10,000 testing examples. So what we're going to be doing is we're going to be building a computer vision model to find patterns in the training data and then use those patterns to predict on the test data. And so let's see a first training example. See the first training example. So we can just index on the train data. Let's get the 0th index, and then we're going to have a look at the image and the label. Oh my goodness. Hold on. The train data. Let's get the 0th index, and then we're going to have a look.
Why didn't then my maybe it's not treated as an array, perhaps? What did I do there?
Look at the image and the label.
Did something there, didn't I? Let's just expand it. Oh, there we go. We have that's let's look at the shape. End object has no attribute size. Then what is label? Oh, label represents how many labels there are then? Because we saw, gosh, the lighting is, this is why I stream in the morning usually. Today I'm streaming in the, off, gosh, it's, almost 5:30 my time. Time flies fast, I guess. When you really enjoy something, you don't realize how fast time goes.
Does not support torch script. So converts a pill into a numpy array, height with color channels in the range 0 to 255 to a torch float tensor of shape. See here? This is what I was talking about, how Pytorch defaults with a lot of transforms to CHW. So color channels first, height, then width in the range of 0 to 1. So typically red, green, and blue values are between 0 and 255, but neural networks like things between 0 and 1. And in this case, it is now in the shape of color channels first, then height, then width. However, some other machine learning libraries prefer height, width, then color channels. Just keep that in mind. We're going to see this in practice later on. So we've got an image and a label. Let's check out some more details about it. Remember how we discussed, oh, there's our label, by the way. So 9, we can go train data.classes, find some information about our class names. Class names. Beautiful. So number 9 would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this particular tensor seems to relate to an ankle boot. How would we find that out? Well, one second. I'm just going to show you one more thing. Class to IDX. Let's go train data.class to IDX. What does this give us? Class to IDX. This is going to give us a dictionary of different labels and their corresponding index.
Okay. Class 2 index.
So if our machine learning model predicted 9, class 9, we can convert that to ankle boot using this attribute of the train data. There are more attributes that you can have a look at if you like. You can go train data dot, and I just push tab to find out a bunch of different things. You can go data, there's the data, that'll be the images, and then I believe you can also go targets. So targets, that's all the labels, which is one big long tensor. Now let's check the shape. Check the shape of our image. So image.shape and label.shape. What are we going to get from that? Oh, label doesn't have a shape. Why is that? Well, because it's only an integer.
Also, this says that the first image is angle boot. The second one is a t-shirt. Third one is a t-shirt. The last element is the last image is a sand.
So, oh, beautiful. Look at that. So our image shape is we have a color channel of 1. So let me print this out in something prettier. Print
I guess that's because it's a what's the technical term? Grayscale image, right?
image shape, which is going to be image shape. Remember how I said it's very important to be aware of the input and output shapes of your models and your data? It's all part of becoming one with the data. So that is what our image shape is. And then if we go next, this is print image label, which is label, but we'll index on class names for label, and then we'll do that. Wonderful. So our image shape is currently welcome back. So in the last video, we covered some of the
Wait, what did I do that?
If there's any errors in the code, please let
I accidentally clicked on something now. No, we didn't reach this area yet.
expected shape of that tensor. So this is one of those scenarios. We're going to print the channels first. Our batch by shape that we'd like for machine learning and output shapes. Just checking the input output shapes, different items of clothing, based to see if we can build a computer vision model to images of t-shirts, trousers, pullovers, dress, shapes of our data as an image. That'd be a faint white one. Sorry to discuss white. Wonderful. So our image shape is currently in the format of color channels height width. We've got a bunch of different numbers that's representing our image. It's black and white. It only has one color channel. Why do you think it only has one color channel? Well, because it's black and white. So if we jump back into the keynote, fashion MNIST, we've already discussed this. Grayscale images have one color channel. So that means that for black, the pixel value is 0, and for white, it's some value for whatever color is going on here. So if it's a very high number, say it's 1, it's going to be pure white. If it's like 0.001, it might be a faint white pixel. But if it's exactly 0, it's going to be black. So color images have 3 color channels, so red, green, and blue. Grayscale have 1 color channel. But I think we've done enough of visualizing our images as numbers. How about in the next video, we visualize our image as an image? I'll see you there. Welcome back. So in the last video, we checked the input-output shapes of our data, and we downloaded the fashion MNIST dataset, which is comprised of images, or grayscale images of t-shirts, trousers, pullovers, dress, coat, sandal, shirt, sneaker, bag, ankle boot. Now, we want to see if we can build a computer vision model to decipher what's going on in fashion MNIST. So to separate, to classify different items of clothing based on their numerical representation. And part of becoming one with the data is, of course, checking the input-output shapes of it. So this is a fashion MNIST dataset from Zalando Research. Now, if you recall, why did we look at our input and output shapes? Well, this is what we looked at before. We have 28 by 28 grayscale images that we want to represent as a tensor. We want to use them as input into a machine learning algorithm, typically a computer vision algorithm, such as a CNN. Then we want to have some sort of outputs that are formatted in the ideal shape that we'd like. So in our case, we have 10 different types of clothing. So we're going to have an output shape of 10. But our input shape is what? So by default, Pytorch turns tensors into color channels first. So we have an input shape of none, 1, 28, 28. So none is going to be our batch size, which of course we can set that to whatever we'd like. And so our input shape format is in NCHW, or in other words, color channels first. But just remember, if you're working with some other machine learning libraries, you may want to use color channels last. So let's have a look at where that might be the case. We're going to visualize our images. So I'll make a little heading here, 1.2. Now this is all part of becoming one with the data. In other words, understanding its input and output shapes, how many samples there are, what they look like, visualize, visualize, visualize. Let's import matplotlib. I'm just going to add a few code cells here. Import matplotlib.pyplot, pyplot as PLT. Now, let's create our image and label, is our train data 0, and we're going to print the image shape so we can understand what inputs are going into our matplotlib function. And then we're going to go plot.imShow, and we're going to pass in our image and see what happens. Because recall, what does our image look like? Image. Our image is this big tensor of numbers. And we've got image shape, 128, 128. Now, what happens if we call plot.imShow? What happens there? Oh, we get an error. What does our image look like? Going into our matplotlib function. And then we're going to go plot.imShow, and we're going to pass in our image and see what happens. Because recall, what does our image look like? Image.
It's an angle boot, right?
And we've got image shape 128, 128. Now, what happens if we call plot.imshow? What happens there? Oh, we get an error. Invalid shape 128, 128 for image data. Now, as I said, this is one of the most common errors in machine learning is a shape issue. So the shape of your input tensor doesn't match the
So we have
expected shape
to
of that tensor.
permute it.
So this is one of those scenarios where our data format, so color channels first, doesn't match up with what matplotlib is expecting. So matplotlib
Color channels first isn't what matplotlib. Okay, I get it. So what we need to do is we need to, let's see if we can figure this out. We just need to permute. How did permute work again? Is it this to it? Yeah, that takes in the first element and puts it last. This goes here, this goes. Yep, and yeah. Yeah, that
just height and width.
I guess if you tilt it this way, that looks like what was I about to say? Yeah, that looks like angle put. What happens if you of course this needs to remain as 2 2 0 1. Does it tilt the image? Hmm. What happened here? This goes to 2, this goes to 0, and this goes to 1. Invalid shape. Wait. No, that didn't do it.
So no color.
Let's just play around with image dot. I mean, a tensor dot permute and see what's the difference. So I'm predicting that with this should go into the second index, right? This should go to the 0th index, and this should go into the first index. What happens if you do 2 1 1? Hmm. At of course 2 1 0. I mean. This is look at the docs of tensor dot permute. So this switches. Oh, it's that doesn't make sense. Returns a view of the original tensor input with its dimensions permuted. Truth. Okay, our original tensor has shape 235. If we permute it, what's gonna happen is if we are gonna permute it to 201. 2 switches to what? The first index. And where does 3 go to? 3 goes to the. Oh, she just made more sense at the beginning of the tutorial. Anyhow, I thought we had figured this out. Touch.permute 201. Okay, now I get it. What it means is when you permute it, make sure that the second dimension comes first, 0th dimension comes second because it's second in this tuple, and the third dimension comes last. No, not the third dimension. The first dimension comes last. In that case, what we have to do is this is our original what shape. So we have to switch this to rand 201. Basically, we want to switch this. So our color channel should appear last. So this should be 0, and this can come as the first and second. All right, and I guess if we flip that, it comes out as this. It flips the axis. Oh, we have a. That's just spam, and but we do have a actual message by what's it? I can't read the name properly with this light. Oh, we have action. Yeah. Hey, I remember you. Hey, hello. How are you? What's up? Actionium was one of my first followers.
Channel for grayscale images, or it also
We have reached day 7 finally. I've come across a long way with machine learning, and yeah, I'm on day 7 now. All good. Yeah, that's great. That's great to hear.
expects the color channels to be last. So we'll see that later on. But for grayscale, we can get rid of that extra dimension
Thank you, Action. Yeah,
by passing an image.squeeze. So do you recall what squeeze
and I
is?
appreciate
To
it
remove
quite a
a
lot.
particular dimension. If we have a look at what goes on now.
We had a raid. Someone raided us. Not someone. Blaze Labs. Or a streamer called Blaze Lab raided our channel. It was 2 days back or something. But other than that, in terms of Twitch, nothing interesting has happened. But in terms of learning, I have learned quite a lot. We made what's it? Of course, I think you were the one who told me you finished the entire course a few years back, right? I finished with the linear regression model, the binary classification model, multi-class classification model, and I'm finally into the image side of things. New what do they call it? CNNs.
Default, we get an ankle boot. Well,
Speed run with amnesia.
that's a very pixelated ankle boot, but we're only dealing with 28 by 28 pixels, so not a very high definition image. Let's add the title to it. We're going to add in a label. Beautiful. So we've got the number 9 here. So where if we go up to here, that's an ankle boot. Now let's plot this in grayscale. How much
Oh wait. Hmm. So we permitted
we
this.
do that? We can do the same thing. We can go plot plt.imshow. We're going to pass in
I mean I forgot things quite a bit, don't I?
image.squeeze, and we're going to change the color map. CMap equals
Alright.
gray. So in Matplotlib, if you ever have to change the colors of your plot, you want to look into the CMap property or parameter, or sometimes it's also shortened to just C.
This
But in
looks
this case,
like some image from outer space with this color scale. Increase YouTube audio. Yeah, I purposefully changed that to what do I have here? I have my mic to 200%. My desktop audio is a bit low. I've been experimenting with my last streams a bit on this volume aspect. Maybe let's do 60%.
imshow is CMap.
Is that better? Can you hear me alongside the YouTube
So we
audio?
have a look at it now. We have an ankle boot, and we can remove the axes too if we wanted to. Plot.axis, turn that off, and the label integer here. So we have a look at it now.
Wait, what? Yeah, okay. Editor me now. It is better. Cool. That's what I like to hear. Um, let's convert this into black and white image. Oh, made a typo there. Why have we? Oh, I guess. Did we squeeze it to get rid of
If you ever have
the?
plt.imshow, we're going to pass in image.squeeze.
I guess that was another way to do it. You don't need the first dimension, do you? Yeah, but I guess permute also works. Just to make it more on side with the tutorial, I'm just gonna squeeze the image instead. Let's look at the image now. Yeah, that looks more like it.
And we're going to change the color map. CMap equals gray. So in Matplotlib, if you ever have to change the colors of your plot, you want to look into the CMap property or parameter, or sometimes it's also shortened to just C. But in this case, imshow is CMap. And we want to plot title. And we're going to put in class names and the label integer here. So we have a look at it now.
Plot or title, okay, yeah, so that we know what the image is now.
We have an ankle boot, and we can remove the axis
Yeah, we have angle put written as the title here. What's that? Want to do a short summary on tensor broadcasting. That's a new term. What is tensor broadcasting? You were the one who recommended me to look into. I forgot the name of the paper, but universal truth or something like that, right? Basically, everything is solved with neural networks. That just blew my mind. Anyhow, what's this? Tensor broadcasting. It's a concept of this technique allows us to perform element-wise operations between two or more tensors of different shapes but having compatible shapes. Hmm. Broadcasting is done when we have different shapes of different. Oh, is this to the universal approximation? Yeah, that's the whatever that you called it. This we make changes to the shape that are compatible by changing the length of the dimension to meet the length of the dimension of the shape of the other tensor. Oh, is this a general term for permute? Is that what you're trying to tell me? Like when you do image dot permute, what I'm basically doing is tensor broadcasting. Yeah, universal approximation. Yeah. Is that what you meant? Permuting, like the general term is tensor broadcasting for that.
too if we wanted to. Plot.axis, turn that off. That's going to remove the axis. So there we go. That's the
It removed the axis. Okay, yeah, of course, we don't need the axis makes the image look a bit ugly. So let's remove it. Let's set it to false. Rather.
type of images that we're dealing with. But that's only a singular image. How about we harness the power of randomness and have a look at some random images from our data set?
Oh, that's not what you meant. So maybe tensor. Maybe I read it wrong. Tensor broadcasting is a different thing, I think. Okay, this finally we have an image to show me what it is. Okay, so we have a tensor here. Huh. Oh, so this tensor was originally 1 into 3, but because of tensor broadcasting, it implicitly means like the code did it automatically, right? A code or whatever technique did it automatically. All right, broadcasting. But due to the mismatch in shapes, it is not possible. So by invoking broadcasting mechanism, we can perform these operations by implicitly adding dimensions with. I see. I see. That's really cool. With you, I always learn new things. So you don't have to squeeze and squeeze. If they are compatible, tensor as arithmetic will happen. Yeah. All right. I understand now. How do you do that with, I guess I have the code for it on you. Torch broadcast tensors. I see. This would be useful when I get more into doing operations on tensors. It's really cool having you here. Like you all always come in and put new terms and new things I'm not aware of.
How would we do this? Let's go plot more images. We'll set a random seed. So you and I are both looking at as similar as possible images, 42. Now we'll create a plot by calling plot.figure, and we're going to give it a size. We might create a 9 by 9 grid. So we want to see 9 random images from our data set. So rows, cols, or sorry, maybe we'll do 4 by 4. That'll give us 16. We're going to go 4
This
I in
needs to be
grid, and we're
lowercase.
going to go 1 to rows times.
ask ChatGPT to help you? Why do I need ChatGPT when I have you? I mean, I like the idea of using ChatGPT and all, but my what is it, policy? I don't think policy is the right word. But anyhow, my belief is that when you want to learn something new, when you want to like get into the field, don't use. Why did my monitor turn off? Don't use chat gpt, especially when you're beginning with learning things like I've seen that a lot of new developers these days, they don't know anything about programming, and they immediately ask they immediately go into chat gpt to code stuff. I mean, chat gpt is great, but if you want to learn something, like really learn it, don't use ChatGPT. Stick to the conventional method of searching things up. And once you get to a certain level in the field, use ChatGPT. ChatGPT is excellent. I won't call you dumb boy. I mean, that's on you itself. You call it yourself that, but yeah, you hallucinate less. That's another thing, right? ChatGPT is just a pro in hallucinating with data. You're brilliant. What I say?
columns plus 1. So
You
we'll
know,
apply what's
I think you know quite a lot more than me in machine learning with the terms that you just bring into stream. Spell check remove the need of dictionaries. Spell check remove the need of dictionaries. We adapt to the tech at hand. I see the analogy that you're putting forward. You're right. Maybe it's just me sticking to the old, because when I started to code, LLM models, like it wasn't ChatGPT wasn't a thing then. Yeah, using ChatGPT is not bad. I agree with you, but when you are kind of like I've seen a lot of new developers these days, they just jump into, like, they don't even know how to use code, and then they just jump into using GPT, and then say, hey, I'm like a developer in the sense they developer with so much experience and all. Yeah, I agree. I mean, don't get me wrong. I'm not saying ChatGPT is bad or anything, but my belief is that when you wanna go into something, immediately jumping onto AI is it's not the best way to learn. It is a way to learn, but at least for me, it's not the best way to learn because of hallucination too. I don't think GPT is at a level there yet where you can ask it to create everything and expect it to be all good. There was a quote, I don't know by whom, but AI is not going to replace developers, but people who use AI are going to replace developers who don't use AI. It's like having a rubber duck with a saw. I mean, yeah, I haven't used ChatGPT to like. Maybe you know what? I need to use it. Yeah, I need to use GPT more. Anyway, not at the beginning, of course. I still stick to that, but maybe I'll give it a go and see how that comes out to be. Yeah, I haven't really used. I do know what a rubber duck is, and like in terms of programming, you have someone to explain your code and stuff, right? But when I get stuck with something, I don't know if it happens with you. Just stop coding for like at least 20 minutes. Come back to the screen, and immediately you get the solution in your head.
going to use.
Whatever you were
We want to see
stuck
16
on.
images or thereabouts. So 16 random images, but used with a manual seed of 42 of our data set. This is one of my favorite things to do with any type of data set that I'm looking at, whether it be text.
What is Daniel doing
Image,
here
audio,
with
doesn't
the
matter. I like
follow?
to randomly have a look at a whole bunch of samples at the start so that I can become one with the data. With that being said, let's use this loop to grab some random indexes. We can do so using Torch's rand int, so random integer, between 0 and length of the training data. This is going to give us a random integer
Let's
in
just
the
look
range
at
of
the
0
tutorial
and however many
first
training
before
samples we
we.
have, which in our case is what? 60,000 or thereabouts. So we're going to create the size of 1, and we want to get the item from that. So that we have a random index. What is this going to give us? Oh, excuse me, maybe we print that out. There we go. So we have random images. Now, because we're using manual seed, it will give us the same numbers every time. So we have 37542, 37542. And then
Yeah.
if we just comment out the random seed, we'll get different numbers every time.
I was wondering why he wasn't using just the random model for that. That answers it.
But this is just to demonstrate. We'll keep the manual seed there for now. You can comment that out if you want different numbers or different images, different indexes each time. So we'll create the image and the label by indexing on the training data at the random index that we're generating. And then we'll create our plot. So fig, or we'll add a subplot. Fig add subplot. And we're going to go rows, cols, I. So at the ith index, we're going to add a subplot. Remember we set rows and columns up to here.
Oh,
And
so
we
he
go
can.
here, InShot.
That makes sense. So you can see all the images at once. That's why he has rows and columns as variables there. Time flies. It's almost gonna be 6 in the evening now.
We're going to show what? We're going to show our image, but we have to squeeze it to get rid of that singular dimension as a color channel. Otherwise, we end up with an issue with matplotlib. We're going to use a color map of gray so it looks like.
Yep. Why do we end up with an issue? Because Matplotlib, unlike Pytorch, wants the color channel to be at last.
The image we plotted above. And then for our title, it's going to be our class names indexed with our label. And then we don't want the axes because that's going to clutter up our plot. Let's see what this looks like.
Although let's just have the access first just to see what it looks like. We got an error. Has no attribute image show. Oh, it's I am show. Okay, it's not image show, although we pronounce it image show. Uh, I'm sorry. What? I mean, what do you mean by that? Uncle. Okay. Now I understand why we turn off the access. It just looks way ugly with the access turned off. And there you go. So is there a way to, because our text is like on top of the image?
Oh my goodness, look at that. It works first go.
Hmm. Oh, maybe it's just my. Nah, I thought it was something to do with my image, with my screen size. But
Usually visualizations take a fair bit of trial and error.
I
We
guess
have
it's
boots,
fine
we have
for now.
shirts, we have bags, we have ankle boots, sandal, shirt, pullover. Oh, do you notice something about the data set right now? Pullover and shirt.
A shirt has, I think that's buttons there, right? Those black dots, and a pullover is just, I guess, pullover is what I am wearing right now. Just here we call it in India we call it a t-shirt, but I guess is pullover a t-shirt? Uh, let's see our labels. I just wanna, yeah. Now they have a t-shirt. They call it a t-shirt or a top. So maybe pullover is something else which I'm not aware of. Or maybe pullovers are like, they cover your like, what's it? Your entire arms.
To me, they look quite similar. Do you think that will cause an issue later on when our model is trying to predict between a pullover and a shirt? How about if we look at some more?
What issue? Sorry.
So we have ankle boots, we have shirts, we have bags, we have ankle boots, sandal, shirt, pullover. Oh, do you notice something about the data set right now? Pullover and shirt. To me, they look quite similar. Do you think that will cause an issue later on
They look quite similar, although the shirt has. Yeah, they do look quite similar.
when our
In
model is trying to
fact.
predict between a pullover and a shirt? How about if we look at some more images? We'll get rid of the random seeds so we can have a look at different styles. So we have a sandal, ankle boot, coat, t-shirt, top, shirt. Oh, is that a little bit confusing that we have
I guess we'll just comment it out rather than just removing that line. Look at a few. Suddenly, this has turned into a fashion stream. So,
a class with t-shirt and top and shirt? Like, I'm not sure about you, but what's the difference between a t-shirt and a shirt?
I mean, the difference between a t-shirt and a shirt is a bit. Oh, this is a t-shirt. What I'm wearing right now has no buttons or anything. We don't have a shirt. We have a shirt here. Oh, this is from another angle. This one doesn't have buttons in it, but the arm length is quite long. This is turning into a like a fashion channel now.
This is just something to keep in mind. As a t-shirt and top, does that look like it could be maybe even a dress? Like the shape is there? So this is just something to keep in mind going forward. Chances are, if we get confused on our, like you and I looking at our data set, if we get confused about different samples and what they're labeled with, our model might get confused later on. So let's have
Let's see the coverance matrix. I am assuming that's a typo. Coverance matrix. What is that now? Oh, is it coverance? So you'll see that the model will have higher LF for the two coverance covariance matrix. Okay. Well, this is too geek for geek. Covariance matrix is two items in a random vector. There an image. Let's see if there's any Medium article about it. Yeah. Written by Grace Martin. I guess we have to do in deep learning. It's not domain. Who's here? The model? Yeah, sure. Let's see what I'm not see. Hear what you have to say. Um, what's the covariance value? How do you find these things? Like, are you a machine learning engineer? Medium stands for medium sized data burst. That's a good one. Ha, ha, ha. Hmm. Not. What's the concept of covariance? Between each pair of elements, what did you say? We will see that models will have higher error for the two classes. Oh, now you are. Okay, I can't understand whether you're joking or not now. The great idea was to reduce the functionality of the web. Are you for real or let's just see. Medium with the medium. Give users less features. Force them to write in a fixed format and how the hmm. I mean, I haven't used Medium quite a lot to be frank. I don't know how well it works. I just to be really frank with you, I just came across it a minute before in a previous article. So it's easier for readers to read on Medium. Your eyes naturally know where to look at. Seems like you're not a fan of them, huh? Yeah, because they have a fixed format. Hmm. Yeah. Well, I haven't used Medium that much, so I can't comment on it.
Have a look at one more and then we'll go into the next video. So we have sneaker, trouser, shirt, sandal, dress, pullover, bag, t-shirt. Well, that's quite a difficult one. Doesn't look like there's even much going on in that image. But the whole
Huh. And charge? Wait, is Medium? Oh, what? They have membership? I didn't know Medium was paid. So, how did they allow this person to post this? I'm not sure. Maybe I mean there might be people out there who are like more text based rather than just video focused. So maybe that might be a good option for them. It's all about taking the same content and putting it on different areas. Like if people are there on, like if I were an article writer as such, I would put the article on Medium. I'll put it on I don't know anything any other sites other than Medium apparently. But my point is we'll just put it up across multiple website. So we can't blame the people who are like doing that. If that's where the users go, then that's where the creators would go, I guess. Try reading first couple of. Huh. I see. Like they just allow you to get I guess it's a freemium product in that case.
whole premise of building machine learning models to do this would be, could you write a program that would take in the shapes of these images and figure out, write a rule-based program that would go, hey, if it's looked like a rectangle with a buckle in the middle, it's probably a bag.
It would be really hard to do that.
I mean, you
Yeah.
probably could after a while, but I prefer to write machine learning algorithms to figure out patterns in data. So let's start moving towards that. We're now going to go on figuring out how we can prepare this data to be loaded into a model. I'll see you there. All right. So we've got 60,000 images of clothing that we'd like to build a computer vision model to classify into 10 different classes. And now that we've visualized a fair few of these samples, do you think that we could model these with just linear lines, so straight lines, or do you think we'll need a model with nonlinearity? So I'm going to write that down. So do you think these items of clothing, images, could be modeled with pure linear lines, or do you think we'll need nonlinearity?
Hmm. We'll need non-linear. Gosh, I can't pronounce. We need non-linearity, of course.
Don't have to answer that now. We can test that out later on. You might want to skip ahead and try to build a model yourself with linear lines or nonlinearities. We've covered linear lines and nonlinearities before, but let's now start to prepare our data even further to prepare a data loader. So right now, our data is in the form of Pytorch datasets. So let's have a look at it. Train data. There we go. So we have dataset, which is of fashion MNIST. And then if we go test data, we see a similar thing, except we have a different number of data points. We have the same transform on each, we turn them into tensors. So we want to convert them from a data set, which is a collection of all of our data, into a data loader. Recall that a data loader turns our data set into a Python iterable. So I'm going to turn this into Markdown. Beautiful. More specifically, can I spell right? It doesn't really matter, we want to just code right. I'm not here to learn spelling. We want to turn our data into batches, or mini batches. Why would we do this? Well, we may get away with it by building a model to look at all 60,000 samples of our current dataset because it's quite small. It's only comprised of images of 28 by 28 pixels. And when I say quite small, yes, 60,000 images is actually quite small for a deep learning scale dataset. Modern datasets could be in millions of images. But if our computer hardware was able to look at 60,000 samples of 28 by 28 at one time, it would need a fair bit of memory. So we have RAM space up here, we have GPU memory, we have compute memory. But chances are that it might not be able to store millions of images in memory. So what you do is you break a dataset from, say, 60,000 into groups of batches or mini batches. So we've seen batch size before. Why would we do this? Well, one, it is more computationally efficient, as in your computing hardware may not be able to store in memory
Doing two matches.
at 60,000 images in one hit. So we break it down to 32 images at a time. This would be batch size of 32. Now, again, 32 is a number that you can change. 32 is just a common batch size that you'll see with many beginner-style problems. As you go on, you'll see different batch sizes. This is just to exemplify the concept of mini batches, which is very common in deep learning. And why else would we do this? The second point, or the second main point, is it gives our neural network more chances to update its gradients per epoch. So what do I mean by this? This will make more
It gives a neural net. Oh, wait, okay. Let's just
sense when we run a training loop.
it.
But if we were to just look at 60,000 images,
It's more computation efficient. Oh, so that's what a batch size is. So I guess my bread analogy turned out to be wrong.
at one time, we would per epoch, so per iteration through the data, we would only get one update per epoch across our entire dataset. Whereas if we look at 32 images at a time, our neural network updates its internal states, its weights, every 32 images thanks to the optimizer. This will make a lot more sense once we write our training loop. But these are two of the main reasons for turning our data into mini batches in the form of a data loader. Now, if you'd like to learn more about the theory behind this, I'd highly recommend looking up Andrew Ong mini batches. There's a great lecture on that. So yeah, large scale machine learning, mini batch gradient descent, mini batch gradient descent. Yeah, that's what it's called, mini batch gradient descent. If you look up some results on that, you'll find a whole bunch of stuff. I might just link this one. I'm going to pause that. I'm going to link this in there. So for more on mini batches, see here. Now, to see this visually, I've got a slide prepared for this. So this is what we're going to be working towards. This is our input and output shapes. We want to create batch size of 32 across all of our 60,000 training images. And we're actually going to do the same for our testing images, but we only have 10,000 testing images. So this is what our dataset's going to look like batched. So we're going to write some code, namely using the data loader from torch.utils.data. We're going to pass it a dataset, which is our training data. We're going to give it a batch size, which we can define as whatever we want. For us, we're going to use 32 to begin with. And we're going to set shuffle equals true if we're using the training data. Why would we set shuffle equals true? Well, in case our dataset for some reason has order, say we had all the pants images in a row, we had all the t-shirt images in a row, we had all the sandal images in a row, we don't want our neural network to necessarily remember the order of our data. We just want it to remember individual patterns between different classes. So we shuffle up the data, we mix it up. And then it looks something like this. So we might have batch number 0, and then we have 32 samples. Now, I ran out of space when I was creating these, but we got, that was fun, up to 32. So this is setting batch size equals 32. So we look at 32 samples per batch. We mix all the samples up, and we go batch, and we'll have, however many batches we have, we'll have number of samples divided by the batch size. So 60,000 divided by 32, what's that, 1,800 or something like that?
Yeah.
So this is what we're going to be working towards. I did want to write some code in this video, but I think to save it getting too long, we're going to write this code in the next video. If you would like to give this a go on your own, here's most of the code we have to do. So there's the train data loader. Do the same for the test data loader. And I'll see you in the next video, and we're going to batchify our fashion MNIST dataset. Welcome back. In the last video, we had a brief overview of the concept of mini batches. And so rather than our computer looking at 60,000 images in one hit, we break things down. We turn it into batches of 32. Again, the batch size will vary depending on what problem you're working on, but 32 is quite a good value to start with and try out. And we do this for two main reasons. We jump back to the code. Why would we do this? It is more computationally efficient. So if we have a GPU with, say, 10 gigabytes of memory, it might not be able to store all 60,000 images in one hit. In our dataset, because it's quite small, it may be able to, but it's better practice for later on to turn things into mini batches. And it also gives our neural network more chances to update its gradients per epoch, which will make a lot more sense once we write our training loop. But for now, we've spoken enough about the theory. Let's write some code to do so. So I'm going to import data loader from torch.utils.data, import data loader. And this principle, by the way, preparing a data loader, goes the same for not only images, but for text, for audio, whatever sort of data you're working with. Mini batches will follow you along, or batches of data will follow you along throughout a lot of different deep learning problems. So set up the batch size hyperparameter. Remember, a hyperparameter is a value that you can set yourself. So batch size equals 32, and it's practice. You might see it typed as capitals. You won't always see it, but you'll see it quite often. A hyperparameter typed as capitals. And then we're going to turn datasets into iterables, so batches. So we're going to create a train data loader here of our fashion MNIST dataset. We're going to use data loader. We're going to see what the doc string is. Or actually, let's look at the documentation. Torch data loader. This is some extra curriculum for you too, by the way, is to read this data page, torchutils.data, because no matter what problem you're going with deep learning or Pytorch, you're going to be working with data. So spend 10 minutes just reading through here. I think I might have already assigned this, but this is just so important that it's worth going through again. Read through all of this, even if you don't understand all.
What's that? There is something called data augmentation that you can do at this stage. Oh, with what I have learned so far. I've heard of the term data augmentation, but I don't know what that is. The process of artificial generating new data from existing data, primarily to train new machine learning ML models. Ah, so if we have so in a way we could change this was it fashion MNES data set of 60,000 images. If we add a bit of color and maybe tilt it around like how they've done it in this image, we'll get more images. Data augmentation, I guess that's another way of augmentation is another word for generation. So we're basically generating data. Yeah, they're more or less tricked into believing you have more data. Ah, I mean, how do you come across these terms? Is GPT or they just search for them? Or maybe you're more about machine learning than me. That might be it.
All of it, what's going on. It's just, it helps you know where to look for certain things. So what does it take? Data loader takes a data set. We need to set the batch size to something. It's the default of 1. That means that we would create a batch of 1 image at a time in our case. Do we want to shuffle it? Do we want to use a specific sampler? There's a few more things going on. Number of workers. Number of workers stands for how many cores on our machine do we want to use to load data. Generally, the higher the better for this one. But we're going to keep most of these as the default because most of them are set to pretty good values to begin with. I'll let you read more into the other parameters here. We're going to focus on the first 3. Data set, batch size, and shuffle, true or false. Let's see what we can do. So data set equals our train data, which is 60,000 fashion MNIST. And then we have a batch size, which we're going to set to our batch size hyperparameter. So we're going to have a batch size of 32. And then finally, do we want to shuffle the training data? Yes, we do. And then we're going to do the same thing for the test data loader, except we're not going to shuffle the test data. Now, you can shuffle the test data if you want, but in my practice, it's actually easier to evaluate
Remind me again. You are a student, right?
different models when the test data isn't shuffled. So you shuffle the training
Thank
data.
you. I guess yeah, that is the idea. After all, I wanna. It takes time. I can't expect to be an expert in or no one can expect to do things the moment immediately when they want it. Right? It takes time. It takes time to to build a six pack. Similarly, it takes time um, for all the good things, really, doesn't it?
To remove order, and so your model doesn't learn order. But for evaluation purposes, it's generally good to have your test.
Once I get to a point of where I completed a couple of courses, I know about machine learning. I wanna just do lots of projects, but before that, I need to do this. It's not that hard. I mean, you just need to try streaming. It makes you accountable. Whatever do what I do. Stream what you learn. Of course, you need to make sure you have the time and all for it. But if not anything, it makes you damn accountable. Oh, you don't have to stream necessarily. Just upload what you learn onto YouTube. Yeah, for sure. A bonus with streaming is that you might find you know like how I have followers like you might find someone else too. You got Discord. I actually, believe it or not, I don't have Discord set up yet. I have to create it though. Most of of course, I don't need to tell you that there are people out there on Twitch who come in there to sell followers and everything, and they ask for this and all. But I have to set this up. I have to set up Discord. Da, da, da. Telegram. Again, I have to set it up for my content creation thing. Um, would Instagram do? Do you have Instagram? If you have Instagram, I can share that. I have. But answer that first, and I'll share.
Data in the same order. because our model will never
If you
actually
have
see
it,
the
I'll
test
share my Instagram with you.
data set during training. We're just using it for other.
Uh, it's not like a normal Instagram. It's a thing that I used for. That is one thing I. Yeah, WhatsApp. Hmm. You know what? I'll set up Discord so I can link it below, like today. So yeah, maybe you can connect with that tomorrow. I haven't actually thought about it though. Like setting up a server and everything Discord. It is personally I don't have a personal Instagram account. I'll show you one thing. Yeah. Hmm. It takes some. What did I call it? There was a code at the end. Was it? There we go. This was a project that I created. It just takes what a meme. Like it doesn't use AI at all. It just takes a meme. It takes those repeatable, loopable song, and then adds a background. You slap those three things together, you got yourself a shot. I called it the automated meme generator. I created an Instagram specifically for this, although I didn't develop that much further. You know what? Maybe making this into a project would maybe that should be my first video on YouTube. Now I just do live streams. What is being streamed now is actually being sent to YouTube itself. If you go down, you'll see my channel.
Valuation. So the order doesn't really matter. The test data loader. It's just easier if we don't shuffle it because then
Vision models are going to kill digital creations. You mean like I can't remember anything on top of my mind. There was a shit panda thing. I don't remember the name of that model. It's not Sora like the one from ChatGPT. Yeah, Mid Journey. Yeah, the logo of a ship. You mean things like that, right? Flux. Yeah. I recently saw a video from Fireship on that. Yep. Sora is from. Let me turn on the lights here. Yeah, Sora is from GPT, isn't it? Again, AI is evolving every day.
then if we evaluate it multiple times, it's not being shuffled every single time. So
I think in that video he mentioned Flux is what was being used behind the scenes for what's it? The model that Elon Musk is like behind Grok, right? I think it's Grok. It's phenomenal. I'm not integrated into Twitter.
let's run that, and then we're going to check it out. Our train data loader and our test data loader.
Yeah, why not? I mean, Elon is behind Grok, right? I mean, I guess he can.
Beautiful. We've got instances of Torch utils data loader, and now
Grok is their LLM. Then what do they use Flux for? I mean, the don't take my word for it. I'm just saying out stuff from what I remember from that video. Flux is VLM. That's a term I'm coming across first. What is that? Video LLM stands for large language model. VLM full form? Is it VLM or vision and language models? Ah, okay. These are diffusers. Diffusers. Diffusion models are. Oh, that's what again I've heard this word uh, thrown around quite a lot. Diffusion models, but now I know that what diffusion models mean generative model. So in a way, is it safe to say that GPT is a diffusion model then? Because GPT generates text and everything, right? Yeah, different architecture because they specialize in images. No, okay, then I'm wrong. Uh, difference between LLMs and diffusion models. LLMs are using text modality. Oh, okay, so there's a clear cut difference here. Diffusion models is to image and videos, whereas LLMs is to text as such. So, what do they call? Is it safe to say diffusion models are also used to create audio as such? Again, I've heard the word transformer too. Had to search it up. Transformer and AI means type of neural network architecture, like what we're doing right now, that transforms. So, transformers are just another word for neural networks, I guess. That input into output. Yep. No, not widely. A fun fact. I got out of sync there. That's my train of thought. Anyhow, you learn something new every day.
Well, let's check out what we've created, hey? I always like to print different attributes of whatever we make. Check out what we've created. This is all part of becoming one with.
Last month, a new paper came showing that diffusers can work with text now. So you will see text diffusers. Oh, is that the reason why when we generate an image with AI, they really can't like whenever they like if I ask AI to create an image of a logo or something, it messes up on the text part. Is that the reason why? So with these text diffusers, we'll accurately be able to put text onto images and stuff. Flux does not, yeah. That's yeah. The Flux does not based on that video again from Fireship. Alright. You learn something new every day, huh?
The data.
I guess a thing with machine learning is, well, I could argue this to be the same for with all things tech, but especially with AI, you need to be on top of all these things. How do you keep in track of all the new papers and stuff that comes out?
So print F. I'm going to go data loaders and
You know, I haven't set up is it I haven't set up the chat what is it the chat overlay on this thing yet on my coding version too. Which one do you like, by the way? I made I switched to coding version 2 because the text and everything was just blurred when I saw my videos. I mean, I like to think of I mean, think of it like ADHD would be a like a gift of sorts, right? Because I've heard, I don't know this, but I'm just saying people with ADHD would be like very creative, right? So when I start doing,
then pass in. This is going to output basically the exact same as what we've got above. Test data loader. And we can also see what attributes we can get from each of these by going train data loader. I don't need caps lock there. Train data loader, full stop, and then we can go tab. We've got a whole bunch of different attributes. We've got a batch size. We've got our data set. We want to drop the last, as in if our batch size overlapped with our 60,000 samples, do we want to get rid of the last batch? Say, for example, the last batch only had 10 samples. Do we want to just drop that? Do you want to pin the memory? That's going to help later on if we wanted to load our
oh, what do we have to do
data
it
faster.
in
A
here?
whole bunch of different stuff here. If you'd like to research more,
Oh yeah, we're creating the train data loader. Passing the train data. Batch size. And random, ask it randomize the data with shuffle. I mean, I've always wanted to do this, stream. Like, this started, like me, thinking on, starting the streaming and stuff started like years back, in fact, but I finally got the courage and everything to quit my 9 to 5 to get into this. So, yeah, there was a great deal of opportunity cost involved.
or you can find all the stuff about what's going on here in the documentation. But let's
Nice.
just keep pushing forward. What else do we want to know? So let's find the length of the train data loader. We'll go length, train data loader. So this is going to tell us how many batches there are. Batches of, which of course is batch size. And we want print length of test data loader. We want length, test data loader, batches of batch size.
Quick question, if you don't mind. How did you find me? Was it through you were just randomly scrolling on Twitch, or how did you like find me?
So let's find out some information. What do we have? Oh, there we go. So just we're seeing
What am I supposed to do here? Yeah.
what we saw before with this one. But this is more interesting here. Length of train data loader. Yeah, we have about 1,875 batches of 30.
Oh, you printed it out on a separate.
So if we do 60,000 training samples divided by 32, yeah, it comes out to 1875. And if we do the same with 10,000 for testing samples of 32, it comes out at 313. This gets rounded up. So this is what I meant, that the last batch will have maybe not 32 because 32 doesn't divide.
Oh, are you like Indian too, or?
Evenly into 10,000. But that's okay. And so this means that our model is going to look at 1800.
True, I mean, really. Now, come to think of it, I guess it's because we have Indian streamers too, but I don't see Indian streamers on. Come to think of it, I haven't seen Indian streamers do like this really. They just are more focused on to gaming as such. Oh, you're there far out in the north. I'm from Kerala. I didn't know you were Indian else. Yeah, I'm from
75
Kerala,
multiple
by the
batches
way.
of 32 images rather than just one big batch of 60,000 images. Now, of course, the number of batches we have will change if we change the batch size. So we have 469 batches of 128. And if we reduce this down to one, what do we get? We have a batch per sample. So 60,000 batches of one, 10,000 batches of one.
I've always wanted to. Oh, you were in Kerala, huh? Oh my god, that's where I'm from. Cochin, yeah.
We're going to stick with 32.
Let me guess. Your parents had. Are your parents in some government job or something? Backwaters 5 star.
But now let's visualize. So we've got them in train data loader. How would we visualize a batch or a single image from a batch? So let's
Did you study in Kendriya Vidyalaya.
Let's show a sample. I'll show you how you can interact with a data loader. We're going to use randomness as well. So we'll set a manual seed and we'll get a random index. Random IDX equals torch rand int. We're going to go from 0 to length of train features batch. Oh, where did I get that from? Excuse me.
Okay, now, we might have studied in the same institution that, um, was it KV Port Trust or Naval Base? Again, my, monitor just went off again. Bharat ka surname Gaurav. I didn't catch that reference, to be frank. Uh,
Getting ahead of myself here.
oh, you were in Qatari Bagh, huh? I was in Port Trust. Oh my god, this is that was the morning song in KVS. Huh. I just did my +1 and +2 from the 11th and 12th.
I want to
Gosh, it's been so long.
check out what's inside the training data loader. We'll check out what's inside.
It's highly coincidental to think you were just like just a few meters from me. Yeah, touch dot manual C. Crazy, huh? The goes to show that the it's a small world. Yeah, oh Jinx. Just said small world and you just messaged the same. True. That's true for sure. I really want to visit Jammu and Kashmir one day.
Inside the training data loader because the test data loader is going to be similar. So we want the train features batch. So I say
Oh,
features.
what happened here? Name train features batch is not defined. What did I do? Yeah. I just mindlessly called it that, didn't I?
Images themselves.
No, this year it's not calmed down. What is not calmed down? Are you talking about the weather?
And the train labels batch is going
Zenska. Is that a place in Germany? Oh, it's in where's this? Kargil district. My friend has gone to Germany. He told me it was really great. I don't know exactly where he went to though. The pictures look beautiful. Oh, look at that. With pollution and all, it's really hard to see such scenes these days. These days. Yeah. It's in Kashmir.
to be the labels of our dataset or the targets in Pytorch terminology. So next iter data loader.
People are so sweet. That's not a thing you hear every day. The only states that I've went outside India are just Bangalore, and Bangalore and no, sorry, by state I mean Bangalore is a city, of course. The two states that I went to, I guess one of them is the Union Territory, Karnataka and Pondicherry.
So because our data loader has
Oh, what is this
1875,
supposed to do now? Oh yeah, we have to create this, don't we? Yeah, for sure. I must go that. I surely got that. One time I'll surely will. It's in my bucket list. Oh yeah, let's create a train features batch. Basically, we're creating a batch, and I guess he's just calling it train features batch. Oh, features and labels. Gotcha. Inputs and outputs, basically.
Torch terminology. So next iter data loader. So because our data loader has 1875 batches of 32, we're going to turn it into an iterable with iter, and we're going to get the next batch with next. And then we can go here, train features, batch.shape, and we'll get train labels batch.
What happened here? Random argument size must be tuple of int, not 10. You can get your streams in real life stream. I guess people do that, don't they? I guess at that point I might just do vlogs instead. Let's see what the shape of this is.
Shape. What do you think this is going to give us? Well,
Yeah, I need tuple although. Well, let's just go forward with the videos. We'll see. So we have 32 batches, one color channel of the image size is 28 pixels wide and 28 pixels high. The is a shape for the features and the output is of course just 32.
there we go. Look at
Okay,
that. So we have a tensor.
it's an array with
32
32
samples. So this is batch size. And this is color
32
change. And this
elements.
is height. And this is width. And then we have 32 labels associated with the 30.
Oh, argument tuple must be tuple of integers, not int. Oh, because yeah, because it's a size. Okay, let's just remove that for a time being. Okay. Ah, oh, of course, it needs a comma around it, doesn't it? Register as a tuple. From to be less than 2, but got from 0. From should be less than 2.
Degree
I
samples.
didn't
Now,
get
we haven't
it.
seen this before.
Let's
Okay.
just continue
Well,
with the
input and output shapes. So we have
tutorial.
shape equals 32, 28, 28, 1. So this is color channels last, but ours is currently in color channels first. Now, again, I sound like a broken record here, but these will vary depending on the problem you're working with. If we had larger images, what would change? Well, the height and width dimensions would change. If we had color images, the color dimension would change. But the premise is still the same. We're turning our data into batches so that we can pass that to a model. Let's come back. Let's keep going with our visualization. So we want to visualize one of the random samples from a batch, and then we're going to go image label equals train features batch, and we're going to get the random IDX from that, and we'll get the train labels batch, and we'll get the random IDX from that. So we're matching up on the, we've got one batch here, train features batch, train labels batch, and we're just getting the image and the label at a random index.
Let's just got it and then we'll try to understand. What is Oh, I think.
within that batch. So, oh, excuse me, I need to set this equal there. And then we
Nah, never mind. Let's just see what this index results in the. Okay, okay, I understand. I mean, it's just give. Why did I overthink this? It's just giving a random integer from. Basically, we're just picking a random index. Yeah, I don't know why I overthunk it though. I don't know even if overthunk is a word. Wait, what did you change? I think I didn't. Maybe it was the. I need to specify the size. Yeah, by default, let's check what the size is. No, torch random. By default, the size is. Oh no, it's not a keyword argument. You need to give it the size. So I don't think I provided it with the size that was needed. So hence, we result in an error. And we just take the random index from this by using dot item.
we're going to go.
There we go. We have a
In
random
show.
index
What are we going to show?
now.
We're going to show the
Although not random with our manual C.
it to remove
I guess that I hope that answers your
right?
question.
And then we'll go plt.title. We'll set the title.
And now let's take a random image. Alright, glad to hear that. I need to get some kind of, you know, like a, not an IC, but what do they call a standing niche? They call it a neck cooler, do they? The thing is that if I put on the fan would just mess up my audio. And it just gets so hot in here. I mean, I don't need to tell you, you've been to Kerala, right? Pain levels, patch. Oh, question for you. I've always wondered, do they like in what's it in Himachal and all like that area in Jammu and Kashmir? Do you really need water cooler and stuff for CPUs? Like, I don't think it's needed, right? Like the weather is when should be called there, right?
Title, which is going to be the class names indexed by the label integer, and then we can turn off the accesses.
Something I've just wondered. The map is-
You can use off here, or you can use false.
Let's
Depends
use
what you'd like to
false.
use. Let's print out the image size, because you can never know enough about your data. And then print. Let's also get the label, and label shape, or label size. Our label will be just a single integer, so it might not have a shape. But that's okay, let's have a look. Oh, bag, see, look, that's quite hard to understand. I wouldn't be able to detect that that's a bag. Can you tell me that you could write a program to understand that? That just looks like a warped rectangle to me. But if we had a look at another one, we'll get another random, oh, we've got a random seed, so it's going to produce the same image each time. So we have a shirt, okay, shirt. So we see the image size there, 128. Now, recall that the image size is a single image, so it doesn't have a batch dimension. So this is just color channels, height, width. We'll go again. Label 4, which is a coat. And we can keep doing this to become more and more familiar with our data. But these are all from this particular batch that we created here. Coat, And we'll do one more, another code. We'll do one more just to make sure it's not a code. There we go, we got it back. Beautiful. So we've now turned our data into data loaders. So we could use these to pass them into a model, but we don't have a model. So I think it's time in the next video, we start to build model 0. We start to build a baseline. I'll see you in the next video. Welcome back. So in the last video, we got our data sets or our data set into data loaders. So now we have 1,875 batches of 32 images for the training data set, rather than 60,000 in one big data set. And we have 313 batches of 32 for the test data set. Then we learned how to visualize it from a batch, and we saw that we have still the same image size, one color channel, 28, 28. All we've done is we've turned them into batches so that we can pass them to our model. And speaking of model, let's have a look at our workflow. Where are we up to? Well, we've got our data ready. We've turned it into tensors through a combination of Torch Vision transforms, Torch utils data.dataset. We didn't have to use that one because Torch Vision.datasets did it for us with the fashion MNIST dataset, but we did use that one. We did Torch utils.data, the data loader, to turn our data sets into data loaders. Now we're up to building or picking a pre-trained model to suit your problem. So let's start simply. Let's build a baseline model. And this is very exciting because we're going to build our first model, our first computer vision model. Albeit a baseline, but that's an important step. So I'm just going to write down here. When starting to build a series of machine learning modeling experiments, it's best practice to start with a baseline model. I'm going to turn this into Markdown. A baseline model. So a baseline model is a simple model you will try and improve upon with subsequent models/experiments. So you start simply, in other words, start simply and add complexity when necessary. Because neural networks are pretty powerful, right? And so they have a tendency to almost do too well on our data set. That's a concept known as overfitting, which we'll cover a little bit more later.
Hey, what?
You start simply, in other words, start simply and add complexity when necessary. Because
A baseline model is a simple model you will try and improve upon with subsequent model/experiment.
neural networks are pretty powerful, right? And so they have a tendency to almost do too well on our data set. That's a concept known as overfitting, which we'll cover a little bit more later. But we build a simple model to begin with, a baseline. And then our whole goal will be to run experiments according to the workflow, improve through experimentation. Again, this is just a guide. It's not set in stone, but this is the general pattern of how things go. Get data ready, build a model, fit the model, evaluate, improve the model. So the first model that we build is generally a baseline. And then later on, we want to improve through experimentation. So let's start building a baseline. But I'm going to introduce to you a new layer that we haven't seen before. And that is creating a flatten layer. Now, what is a flatten layer? Well, this is best seen when we code it out. So let's create a flatten model, which is just going to be nn.flatten. And where could we find the documentation for this? We go nn flatten. Flatten in Pytorch. What does it do? Flattens a contiguous range of DIMs into a tensor for use with sequential. So there's an example there, but I'd rather, if in doubt, code it out. So we'll create the flatten layer, and of course, all nn.flatten or nn. Modules could be used as a model on their own. So we're going to get a single sample. So x equals train features batch. Let's get the first one, 0. What does this look like? So it's a tensor. X. Maybe we get the shape of it as well. X shape. What do we get? There we go. So that's the shape of x. Keep that in mind when we pass it through the flatten layer. Do you have an inkling of what flatten might do? So our shape to begin with is what? 128, 28. Now let's flatten the sample. So
Flattening a list is just converting a list or an array of arrays into a single array. So I guess it would convert this tensor into an array with dimensions 1 into 28 into 28. And let me see if I can do this on top of my head. 28 times 28 is, let's bring my Indian out. 224, 784. I think it's is it 784? Yeah, I think it's 784. Let's see if I got that right.
output equals, we're going to pass it to.
I mean, of course, I just guessed that's what flatten does, but let's see if I got that arithmetic right. Yeah, there we go.
The flatten model, x. So this is going to perform the forward pass internally on the flatten layer. So perform forward pass. Now let's print out what happened. Print out what happened. Print shape before flattening equals x.shape. And we're going to print shape after flattening equals output.
Flatten model. Yeah, let's see. I'm just
flatten model and
purely guessing. Yeah.
Oh.
There we go. We were right. I guess we left off one there, but it's alright.
You notice what happened? Well, we've gone from 12828 to 1784. Wow, what does the output look like? Output. Oh, the values are now in all one big vector. And if we squeeze that, we can remove the extra dimension.
Yeah.
So we've got one big vector of values. Now, where did this number come from? Well, if we take this, and this is, what shape is it? We've got color channels, we've got height, we've got width. And now we flattened it to be color channels, height, width. So we've got one big feature vector because 28 by 28 equals what? We've got one value per pixel, 784. One value per pixel in our output vector. Now, where did we see
one value per pixel? So maybe I guess just by combining what each pixel says, the model predicts whether like what the image is basically.
See this before. If we go back to
Yeah,
Arduino, we have a look at Tesla's, takes 8
it
cameras and
is
then it turns it into a three-dimensional vector space.
right.
Vector space. So that's what we're trying to do here. We're trying to encode whatever data we're working with. In Tesla's case, they have 8 cameras. Now theirs has more dimensions than ours because they have the time aspect because they're dealing with video and they have multiple different camera angles. We're just dealing with a single image here. But regardless, the concept is the same. We're trying to condense information down into a single vector space.
Hmm.
And so if we come back to here, why might we do this? Well, it's
Oh yeah, of course. You mean okay. You mean it's very important to understand dimensions, right? Yeah, yeah, of course.
because we're going to build a
I mean, it's not the same, but what I meant was the our calculation turned out to be right.
baseline model and we're
I
going
guess if you flatten this again, by theory, it will just return. Flattening this would be same as squeezing it.
to use a linear layer as the baseline model. And the linear layer can't handle multi-dimensional data like this. We want it to have a single vector.
All right, let's try it then. See. So this is our output. Let's print output dot shape and let's print it out. And we're gonna have our output 2, which is we're just gonna flatten our earlier output that we got. So this should result in the shape just with just 784, right? Let's see. Print and okay. Maybe I was wrong. It is not same as squeezing it. Then let's try another. Maybe one is like by default it exists. Let's try another experiment. Let's create a tensor. We're back to the basics now. Torch dot rand, right? Rand tensor, yeah. Let's create a random tensor with the size. So what I'm trying. Okay, let's just do the size as. Okay. So I'm predicting that when we flatten this would convert into a tensor with size 1 comma 3 comma 9, and once we flatten that again it would be 1 comma 27, but maybe that might be the limit, and then that one would just exist maybe like by default. Totally predicting this, so let's see what comes out of this now. So let's do this. Let's replace output with output will remain as output. Haha, this is fun indeed. Yeah. Oh no, wait. Huh. Okay. Maybe I was wrong then. Hmm. Interesting. So what happens if you remove you don't give a first dimension? It just adds the dimension by default, maybe? Wait, what? Interesting. It doesn't go beyond like the it doesn't change the first dimension. You know what? Let's just print t, and here let's print the along with the shape. Let's just print output. We don't need output to us because it would be. Oh, you know what? Let's just print output. So back to the basics again. Okay, this is outer bracket, and this has 1 2. Well, we are to include this entire thing. And then 3. Okay. And inside each, we have three arrays: one, two, three, one, two, three, one, two, three. And inside each, we have three elements: one, two, three. So we have a tensor with size 3 to 3 into 3. When we flatten it, what happens is that we have this. Okay, the brackets here just get removed. Like this gets deleted, this gets deleted, this gets deleted. You know what? If I just copy this, bracket tables, it just removes this. This is what flattening an array is, right? This is no this much, anyways. Is this what? Yeah, there we go. But we can't further flatten this because apparently the outermost. Actually, why can't we further flatten this? So what would further flattening this look like? Right. Yeah, but my it's a stack of three images. It's called flatten because it flattens it into a stack of images. Oh, three images as in one image for RGB. Maybe is that? I'm just guessing. Yeah. Okay, okay. No, I get the point. So maybe that's why it doesn't because we only have one color channel here. That's why this one wasn't removed. Not a color channel. It's a grayscale image. That's just black and white. Yeah, but with an actual image, I guess this is what it would look like, right? I guess guessing this is the height and width. This gets multiplied, and we have three images of sorts. Huh. That's really interesting. But in theory, if I really want to, how would I convert this? Let me try to figure this out. How would we convert this and just remove this? Hmm. Or in other words, convert the shape from 3 3 to. I guess this is okay. Think, Shahjahan, think. So we need to remove this. There was a function in the basics, right? It was not permute, it was before that. It was not squeeze or unsqueeze. There was a method. Unsqueeze takes index. But unsqueeze only works for like the dimension should be one. With one, yeah, I agree. You can just remove it. I'm saying for this, right? Fun exercise. Now do it in reverse and add back the dimensions. Hmm. Wait a second. Let me just figure this out. This is interesting. So the task here is to remove these brackets. I know there's a method for this. It was in that covered in the basics. Reshaping, yeah, reshaping. Torch dot reshape. Is that the method? Oh yeah. So this is how many elements are there at the end? I'm just gonna remove this for the time being. Oh, never mind. We have the shape printed out anyways. I can't see the shape. Oh no, there we go. So it's 3 9, right? So we want to make this 3 into 9 is what? It is 27. There are 27 elements in this. So, output 2 dot view. The reason I'm using view is because reshape would affect the like original output too. Anyway, I need to view this as can I just do 27? Maybe I need to give it as a tuple first, and 27 is in val for maybe 1 comma 27 would work. It says that what just happened here? Oh, of course. I was experimenting with this. That should okay. All right. There we go. We resolved it. We flattened it into a list. So we had to use view or reshape. This was really interesting, wasn't it?
as input. Now this
Anyhow,
after
we
we've coded up
went along a bit of tangent there.
our model.
Let's
Let's do
just
that. From torch,
quickly finish
import
our goal for today.
we're going to go class, fashion, mnist, model v0. We're going to inherit from nn.module.
Yeah, let's create our. Well, let's just do this in another line.
Model, and we're going to use a linear layer as the baseline model. And the linear layer can't handle multi-dimensional data like this. We want it to have a single vector as input. Now this will make a lot more sense after we've coded up our model. So let's do that. From torch, import nn. We're going to go class, fashion, mnist, model v0. We're going to inherit from nn.module. And inside here, we're going to have an init function.
Define the constructor.
In the constructor, we're going to pass in self. We're going to have an input shape, which we'll use a type int, which will take an integer. Because remember, input shape is very important for machine learning models. We're going to define a number of hidden units, which will also be an integer. And then we're going to define our output shape, which will be, what do you think our output shape will be? How many classes are we dealing with? We're dealing with 10 different classes, so our output shape will
10, right?
be, I'll save that for later on. I'll let you guess.
Come on, let me guess
Shapes are very important for machine learning models. We're going to define a number of hidden units, which will also be an integer. And then we're going to define our output shape, which will be,
there are 10 outputs there, so it should be, it can just be 10 or it can be 110. There should be 10 elements either way.
what do you think our output shape will be? How many classes are we dealing with? We're dealing with 10 different classes, so our output shape will be, I'll save that for later on. I'll let you guess for now, or you might already know. We're going to initialize it. And then
Yeah, because there are 10 type of clothes here, right? I believe there are 10, yeah, 9 indexes or 10 elements.
create our layer stack. Self.layer stack equals nn.sequential. Recall that sequential, whatever you put inside sequential, if data goes through sequential, it's going to go through it layer by layer. So let's create our first layer, which is going to be nn.flatten. So that means anything that comes into this first layer, what's going to happen to it? It's going to flatten its external dimensions here. So it's going to flatten these into something like this. So we're going to flatten it first, flatten our data. Then we're going to pass in our linear layer. And we're going to have how many in features? This is going to
Oh, what's that? He said it will flatten external dimensions.
The input shape. Let's go. If data goes through sequential, it's going to go through it layer by layer. Self.layer stack equals nn.sequential. Recall that sequential, whatever you put inside sequential, if data goes through sequential, it's going to go through it layer by layer. So let's create our first layer, which is going to be nn.flatten. So that means anything that comes into this first layer, what's going to happen to it? It's going to flatten its external dimensions here.
Ah, okay. Yeah, external dimensions. In the first dimension is not included as we saw. Anyhow, that was a fun exercise. I managed to remember what I've learned so far, anyways, with the reshape and all.
So it's going
Reshape
to
view
flatten
and
these
all.
into something like this.
Yeah, right. Hey, we have a third viewer now. Hey, to over came just now.
So we're going to flatten it first.
Haha, yeah. I guess that's the thing about streaming, huh? When you have people point out your mistakes and everything, it just sticks with you more concretely, if that's a word.
Flatten our data. Then we're going to pass in our linear layer. And we're going to have how many in features? This is going to be input shape, because we're going to define our input shape here. And then we're going to go out features equals
I'm
3
gonna predict the output shape is something to do with 10 elements.
units. And then we're going to create another linear layer here. And we're going to set up in features equals hidden units. Why are we doing this?
How many layers is we gonna define for this one? Hidden units. Another layer with the in features as hidden units, and I mean, I'm not sure how many layers he's planning
Out
on
features
making,
equals
so
output
let's
shape. Why are we putting the
check out.
same out features here as the in features?
Oh, just two layers apparently. I mean three if I because we're including flatten also.
Here? Well, because subsequent layers, the input of this layer here, its input shape has to line up with the output shape of this layer here. Hence why we use out features as hidden units for the output of this nn.linear layer, and then we use in features as hidden units for the input value of this hidden layer here. So let's keep going. Let's go def, we'll create the forward pass here, because if we subclass nn.module, we have to override the forward method. The forward method is
Yeah,
going to define what? It's going to define the forward computation of our
yeah,
model. So we're just
that's
going to return
right.
self.layer stack of x.
X, which is gonna be a tensor.
So our model is going to take some input, x, which could be here, x. In our case, it's going to be a batch at a time. And then it's going to pass each sample through the flatten layer. It's going to pass the output of the flatten layer to this first linear layer. Then it's going to pass the output of this linear layer to this linear layer. So that's it. Our model is just two linear layers with a flatten layer. The flatten layer has no learnable parameters. Only these two do. And we have no nonlinearities. So do you think this will work? Does our dataset need nonlinearities?
Oh yeah, I mean, that's the trick question. Hmm. Let's think, yeah. It's hard to say, but I'm not sure, but I'm guessing here. Maybe we don't need rel layers because we can draw lines like these right across each pixel, can't we? I think we can, but I guess well that's my prediction anyways. I don't think we need rel
Well,
layers.
we can
I
add
might be
features of our
wrong,
model to the data.
but
But let's set
let's
up an instance of our model. So torch dot manual seed. Let's go set up model with input parameters. So we have model 0 equals fashion mness model, which is just the same class that we wrote above. And here's where we're going to define the input shape equals 784. Where did I get that from? Well, that's here. That's
there is already a non-linear. There isn't a non-linear layer in use here, right? We are just using two linear layers here. Ah, okay. Gotcha. Anyhow,
The input shape equals 784. Where did I get that from? Well, that's here. That's 28 by 28. So the output of flatten,
I thought it was with activations. Hmm. I guess since this is a multi-class activation, we use softmax here, don't we?
84. Where did I get that from?
I'm just guessing again. He might use some other activation layer.
Well, that's here. That's 28 by 28. So the output
Yeah,
of flatten needs to be the input shape here. So we
that's
could put
right.
28 by 28 there, or we're just going to put 784 and then write a comment here. This is 28 by 28. Now, if we go, I wonder if nn.linear will tell us. nn.linear will tell us what it expects as in features. Size of each input sample, shape, where star means any number of dimensions including none in features, linear weight. Well, let's figure it out. Let's see what happens. If in doubt, code it out, hey? We'll see what we can do. Hidden
I like that motto of his. If in doubt, got it out. It rhymes too.
units equals, let's go with 10 to begin with. How many units in the hidden layer? And then the output shape is going to be what? Output shape is length of class names, which will be 1 for every class. Beautiful. And now let's go model 0. We're going to keep it on the CPU to begin with. We could write device agnostic code, but to begin, we're going to send it to the CPU. I might just put that up here, actually, to CPU. And then let's have a look at model 0. Wonderful. So we can try and do a dummy forward pass and see what happens. So let's create dummy x equals torch rand. We'll create it as the same size of image, just a singular image. So this is going to be a batch of 1, color channel 1, height 28, height 28. And we're going to go model 0 and pass through dummy x. So this is going to send dummy x through the forward method. Let's see what happens.
I mean, this doesn't represent that. Okay, we're just testing out with random tensors, I guess. Wait, it has non-linearity. If it did not, the two matrices could be collapsed into one. Hmm. It has non-linearity. If it did not, the two matrices. If it has bias. You mean this model has a non-linear layer? Is that what you're saying? Or it needs? Are you saying this has a non-linear layer right now, or it needs a non-linear layer later on? And this Daniel here is just keeping it for in the future.
Okay, wonderful. So we get an output of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 logits. Beautiful. That's exactly what we want. So we have one logit value per class that we have. Now, what would happen
Logit, what are logits? Just raw outputs of the model.
if we got rid of flatten? And then we ran this, ran this, ran this. What do we get? Oh, mat1 and mat2 shapes cannot be multiplied. So we have 28 by 28 and 7.
Oh, that's
Okay, what
very
happens if we
flattering,
change
huh?
our input shape to 28? We're getting shape mismatches here. What happens here? Oh, okay, we get an interesting output. But this is still not the right shape, is it? So that's where the flatten layer comes in. What is the shape of this? Oh, we get 1, 1, 28, 10. Oh, so that's why we put in flatten, so that it combines it into a vector. So we get rid of this. See if we just leave it in this shape, we get 28 different samples of 10, which is not what we want. We want to compress our image into a singular vector and pass it in. So let's reinstantiate the flatten layer, and let's make sure we've got the right input shape here, 28 by 28. And let's pass it through. Torch size 110. That's exactly what we want. One logit per class. So
Yep.
this can be a bit fiddly when you first start, but it's also a lot of fun once you get it to work. And so just keep that in mind. I showed you what it looks like when you have an error. One of the biggest errors that you're going to face in machine learning is different tensor shape mismatches. So just keep in mind the data that you're working with, and then have a look at the documentation for what input shape certain layers expect. So with that being said, I think it's now time that we start moving towards training our model. I'll see you in the next video. Welcome back. In the last video, we created model 0, which is going to be our baseline model for our computer vision problem of detecting different types of clothing in 28 by 28 grayscale images. And we also learned the concept of making sure, or we rehashed on the concept of making sure our input and output shapes line up with where they need to be. We also did a dummy forward pass with some dummy data. This is a great way to troubleshoot to see if your model shapes are correct, if they come out correctly, and if the inputs are lining up with where they need to be. And just to rehash on what our model is going to be, or what's inside our model, if we check model 0 state dict, what we see here is
Check command 2.
that our first layer has a weight tensor, It also has a bias, and our next layer has a weight tensor, and it also has a bias. So these are, of course, initialized with random values, but the whole premise of deep learning and machine learning is to pass data through our model and use our optimizer to update these random values to better represent the features in our data. And I keep saying features, but I just want to rehash on that before we move on to the next thing.
Oops, again, my secondary monitor just went off when I was reading your message. Yep. What's that? It might be hallucinating, but what I remember, oh, sorry, not that. I might be hallucinating, but what I remember is that the hidden layer has activations which give it the behavior we are looking for. In vector calculus, we can calculate, compress matrix multiplication into one matrix. M into n into p is equal to r of result matrix. Let me just read that once more. I might be hallucinating. But the hidden layer has activations. The hidden layer has activations. I mean, I can't comment on that because I am not sure. But mm, we would be giving like this logits, the raw outputs that we get, we would be converting that into predictions through some this thing, like through some activation what is it? Activation functions like sigmoid, not sigmoid in this case. Sigmoid is for binary classification. We use it for binary classification. I guess we use softmax for this one. Yeah, Relu. So if we keep adding as much layers as we want, if we don't have activations, it's equal to one layer. Or you're saying without adding an activation layer, um, adding just keeping on adding activate like just keeping on adding layers is not is going to be same as if we just have one layer. I'm not sure if that makes any sense from what I'm saying.
Feature in data could be almost anything. So, for example, the feature of this bag could be that it's got a rounded handle at the top. It has a edge over here, it has an edge over there. Now, we aren't going to tell our model what features to learn about the data. The whole premise of it is to, well, the whole
Ah, okay. 100%. Ah, okay, maybe that is I see, I see. Um okay, I understand. I guess that makes sense. It's like this, right? Even if we keep on adding a hidden layer, this is output layer, input layer. Even if we had 8 or 7 different layers, that is same as adding one layer if we don't have an activation function. I will experiment with it. That is useful
fun, the whole magic
information.
behind machine learning
Yeah.
is that it figures out what features to learn. And so that is what the weights and bias matrices or tensors will represent, is different features in our images. And there could be many because we have 60,000 images of 10 classes. So let's keep pushing forward. It's now time to set up a loss function and an optimizer. Speaking of optimizers, so 3.1, set up loss, optimizer, and evaluation metrics. Now, recall in Notebook 2, I'm going to turn this into Markdown, we created, oh, I don't need an emoji there. So this is, by the way, we're just moving through this workflow. We've got our data ready into tensors. We've built a baseline model. It's now time to pick a loss function and an optimizer. So if we go back to Google Chrome, let's write here, loss function. What's our loss function going to be? Since we're working with multi-class data, our
Is he
loss function will be nn dot cross entropy loss.
yeah,
And our
course.
optimizer,
Okay.
we've got a few options here with the optimizer, but we've had practice in the past with
Yeah, Daniel always uses SGD throughout this
SGD, which stands
tutorial.
for stochastic
I was
gradient
gonna
descent,
just
and
spread
an
it.
optimizer. So our optimizer, let's just stick with SGD, which is kind of the entry-level optimizer, Torch Optim SGD for stochastic gradient descent. And finally, our evaluation metric. Since we're working on a classification problem, let's use accuracy as our evaluation metric. So recall that accuracy is a classification evaluation metric. Now, where can we find this? Well, if we go into learnpytorch.io, this is the beauty of having online reference material. In here, neural network classification with Pytorch. In this notebook, section
Adam is better, but more memory needed. You know, I had when you first came into my stream, I think it was just after that. I tried going into what I watched the video on three blue, one brown on what SGD is, or not SGD, what gradient descent is in general and back propagation is in general. I understand what that is from a math perspective, or at least I think I understand it. But what I've decided is that once I end this, or this is the plan for now, once I finish this tutorial, I may or may not look into the math of all these loss functions and all the optimizers that we're using. Because at the end, if you want to become an expert in machine learning, math is important, however you put it, right? Yeah, of
We created.
course.
Do we have different
Great
classification
idea.
methods? Yes, we did. So we've got a whole bunch of different options here for classification and evaluation metrics. We've got accuracy, precision, recall, F1 score, a confusion matrix. Now we have some code that we could use. If we wanted to use torch metrics for accuracy, we could. And torch metrics is a beautiful library that has a lot of evaluation. Oh, it doesn't exist. What happened to torch metrics? Maybe I need to fix that. Link. Torch metrics has a whole bunch of different Pytorch metrics. So very useful library. But we also coded a function in here.
Just keep in mind the reason for their forms. It's easy to make. It's to make it easily differentiable. Oh, you mean you're explaining how it would help me, right? Yeah.
Which is accuracy FM. So we could copy this straight into our notebook here. Or I've also, if we go to the Pytorch Deep Learning GitHub, I'll just bring it over here. I've also put it in helperfunctions.py. Now this is a script of common functions that we've used throughout the
Yeah,
course.
I mean, I understand what Relu just turns a negative input and it just takes the maximum of zero. Like if it's a negative input, it converts it to zero. Otherwise, just gives back the positive number. And then sigmoid just takes in a thing and just compresses it between 0 and 1.
Including if we find accuracy function here. Calculate accuracy. Now, how would we
They can take many forms. The form they take is determined by how easy it is to differentiate. Ah, okay, alright. Yeah, gotcha. It is, they can take many forms.
get this
Alright,
helperfunctions
yeah.
file, this
Yeah.
Python file, into our notebook? One way is to just copy the code itself straight here. But let's
Oh, what you mean is loss function and optimizer like there are many loss functions and optimizers out there. Is that what you say? Is that what you're saying?
import it as a Python script. So import request, and we're going to go from pathlib import path. So we want to download, and this is actually what you're going to see
All
in
right.
practice
Okay,
in
I
Python
understand.
projects, especially deep learning and machine learning projects, is different functionality split up in different Python files. And that way you don't have to keep rewriting
Okay, he's trying to get the help of.
the same code over and over again. Like, we've written a training and testing loop a fair few times.
I'm just gonna copy that from the previous notebook that we had. Oh, okay. Okay. Now I understand. Relu itself has many variations or variants. Anyhow, so I'm trying to. There we go. We're just gonna install this. I'm gonna copy that, run that.
Well, if we've written it once and it works, we might want to save that to a .py file so we can import it later on. But let's now write some code to import this helperfunctions.py file into our
Haha,
notebook.
yeah,
So
there we go.
download helper functions
Hey to
from
whoever came onto the stream right now.
learn Pytorch repo. So we're going to check if our helper functions.py,
But the one we choose or the winner is. Wait, but the one we choose or the winner is the one which is easy to differentiate. The winner is the one which is easy to differentiate. Oh, but the one that we need to choose varies depending on the problem that we have at hand. Like for is that what you're saying? I think that's what you're saying, isn't it?
if this already exists, we don't want to download it. So we'll print helper functions.py already exists, skipping download, skipping download.
Hmm. The one we okay, then what else does that mean? It's same for all problems. Relu and middle and sigmoid in the end always. Are you trying to say that the position of the layers is always gonna be the same? Is that what you're trying to say? But we have alternative.
Load dot dot dot. And we're going to go else here. If it doesn't exist,
Ah, okay, okay. I see. Okay, I see what you mean. Even though there are different variants, we always go with like you mentioned, there are different variants for Relu. What is it, Jello, things like that. We always end up choosing Relu. Is that what you're saying?
so
Yeah.
we're going to download it.
The
Downloading.
others are just swept away to the side. Yeah.
Helper functions.py. And we're going to create a request here with the request library
Ah,
equals
there we go. Finally, I
request.get. Now,
understood
here's where
what
we
you
have to
meant
pass in the URL of
and
this
what
file.
you're
It's
saying.
not this
Oops, let's just go back.
.py already exists. Skipping download. Skipping download dot dot dot. And we're going to go else here. If it doesn't exist, so we're going to download it. Downloading helper functions.py. And we're going to create a request here with the request library equals request.get. Now, here's where we have to pass in the URL of this file. It's not this URL here. When dealing with GitHub, to get the actual URL to the files, many files, you have to click the raw button. So I'll just go back and show you. Click raw here.
For purpose. Oh yeah, of course, yeah. The others are just there for the yeah, for academic purpose, right? Yeah.
And we're going to copy this raw URL. See how it's just text here? This is what we want to download into our Colab notebook. And we're going to write it in there. Request equals request.get. And we're going to go with open. And here's where we're going to save our helper functions.py. We're going to write binary as file. F is for file. We're going to go f.write request.content. So what this is saying is Python is going to create a file called helperfunctions.py and give it write binary permissions as f. F is for file, short for file. And then we're going to say f.write, hey, request, get that information from helperfunctions.py here and write your content to this file here. So let's give that a shot. Beautiful. So downloading helperfunctions.py. Let's have a look in here. Do we have helperfunctions.py? Yes, we do. Wonderful. So now we can import our accuracy function. Where is it? There we go. Import accuracy function. So this is very common practice when writing lots of Python code is to put helper functions into .py scripts. So let's import the accuracy metric. Accuracy metric.
Because I'm just really tired. I just want to finish off. I'm planning to end the stream at the 16. I mean, so 15 minutes left to go.
From helper functions. Of course, we could have used torch metrics as well. That's another perfectly valid option, but I just thought I'd show you what it's like to import your own helper function script. Of course, you can customize helper functions.py to have whatever you want in there. So see this, we've got from helper functions, import accuracy function. What's this saying? Could not be resolved. Is this going to work? It did. And where you can go accuracy function, do we get a doc string? Seems like Colab isn't picking things up, but that's all right. Looks like it still worked. We'll find out later on if it actually works when we train our model. So set up loss function and optimizer. So I'm going to set up the loss function equals nn.cross-entropy loss. And I'm going to set up the optimizer here, as we discussed before, as torch.optim.sgd for stochastic gradient descent. The parameters I want to optimize are the parameters from model 0, our baseline model, which we had a look at before, which are all these random numbers. We'd like our optimizer to tweak them in some way, shape, or form to better represent our data. And then I'm going to set the learning rate here. How much should they be tweaked each epoch? I'm going to set to 0.1. Nice and high because our data set is quite simple. It's 28 by 28 images. There are 60,000 of them. But again, if this doesn't work, we can always adjust this and experiment. So let's run that. We've got a loss function. Is this going to give me a doc string? There we go. So calculates accuracy between truth and predictions. Now, where does this doc string come from? Well, let's have a look. Helper functions.
Rate is 0.1.
That's what we wrote before. Good on us for writing good doc strings. Accuracy function. Well, we're going to test all these out in the next video when we write a training loop. So, oh, actually, I think we might do one more function before we write a training loop. How about we create a function to time our experiments? Yeah, let's give that a go in the next video. I'll see you there. Welcome back. In the last video, we downloaded our helperfunctions.py script and imported our accuracy function that we made in Notebook 2. But we could really beef this up, our helperfunctions.py file. We could put a lot of different helper functions in there and import them so we didn't have to rewrite them. That's just something to keep in mind for later on. But now, let's create a function to time our experiments. So creating a function to time our experiments. So one of the things about machine learning is that it's very experimental. You probably gathered that so far. So let's write here. So machine learning is very experimental. Two of the main things you'll often want to track are, one, your model's performance, such as its loss and accuracy values, etc. And two, how fast it runs. So usually you want a high performance and a fast model. That's the ideal scenario. However, you could imagine that if you increase your model's performance, you might have a bigger neural network, it might have more layers, it might have more hidden units, it might degrade how fast it runs because you're simply making more calculations. So there's often a trade-off between these two.
Yep, more
And how fast
numbers
it runs
to
will really be
crunch
important if
means
you're
a
running a model,
slower
say, on the internet, or
performance
say on a
rate.
dedicated GPU, or say on a mobile device. So these are two things to really keep in mind. So because we're tracking our model's performance with our loss value and our accuracy function, let's now write some code to check how fast it runs. And I did on purpose above, I kept our model on the CPU. So we're also going to compare later on how fast our model runs on the CPU versus how fast it runs on the GPU. So that's something that's coming up. Let's write a function here. We're going to use the timeit module from Python. So from timeit, import the default timer as, I'm going to call it timer. So if we go Python default timer, do we get the documentation for, here we go, timeit. So
Did not time it was a built-in module. From timeit, and what was the default timer? Let's just
do we have default timer?
play the video
Wonderful.
along.
So the default timer, which is always timed per counter, you can read more about Python timing functions in here. But this is essentially just going to say, hey, this is the exact time that our code started. And then we're going to create another stop for when our code stopped. And then we're going to compare the start and stop times. And that's going to basically be how long our model took to train. So we're going to go def print train time. And this is just going to be a display function. So start, we're going to get the float, type in, by the way, start and end time. So the essence of this function will be to compare start and end time. And we're going to set the torch or the device here. We'll pass this in as torch.device. And we're going to set that default to none because we want to compare how fast our model runs on different devices. So I'm just going to write a little doc string here. Print difference between start and end time. And then, of course, we could add more there for the arguments, but that's a quick one-liner. Tell us what our function does. So total time equals end minus start. And then print, we're going to write here, train time on whichever device we're using. Might be CPU, might be GPU. Total time equals, we'll go to 3, and we'll say seconds. 3 decimal places, that is, and return total time. Beautiful. So, for example, we could do start time equals
Is it missing a space? Oh yeah, there you go. That should fix it. Let's keep that to 3 decimal places. And seconds.
timer, and then end time equals timer. And then we can put in here some code between those two. And then if we go print, train, oh, maybe we need timer like this. We'll find out. If in doubt, code it out, you know. We'll see if it works. Start equals start time, and end equals end time, and device equals, we're running on the CPU right now. CPU. Let's see if this works. Wonderful. So it's a very small number here. So train time on CPU, very small number because the start time is basically on this exact line. Comment basically takes no time to run. Then end time is on here. We get 3.304 times 10 to the power of -5. So quite a small number. But if we put some modeling code in here, it's going to
Oh, we need to call this.
measure the start time of this cell. It's going to model our code in there. Then we have the end time, and then we find out how long our model took to train. So with that being said, I think we've got all of the pieces of the puzzle for creating some training and testing functions. So we've got a loss function, we've got an optimizer, we've got a valuation metric, we've got a timing function, we've got a model, we've got some data. How about we train our first baseline computer vision model in the next video? I'll see you there. Good morning. Well, might not be morning wherever you are in the world. It's nice to know here. I'm up recording some videos because
it's rather opposite. It's not morning at all.
If you're using Google Colab, since I use Google Colab
It's
Pro,
evening
not necessary
now.
for the course, but I just found it worth it.
Random question off topic. Where's the oldest mosque in India? It's in Kerala itself, right? The oldest church is also in India. The oldest church is also in Kerala. Mosque also. It's from memory, by the way. Yeah, it's in my state itself. Hmm. I don't know the exact location though. We can Google it though. Oldest mosque in India. Oh, it's in Kozhikode. Yeah.
for how much I use to do a collab. I get longer idle timeouts, so that means that my collab notebook will stay persistent for a longer time. But
8 more minutes to go till
awesome,
we
nice,
reach
so I can
our
reconnect.
goal for
And then when I want to
today.
get back to wherever we were, because we downloaded some data from torchvision.datasets, I have to rerun all of these cells. So a nice shortcut, we might have seen this before, is to just come down to where we were, and if all the code above works, oh, there we go. I write myself some notes of where we're up to. Let's go run before. So this is going to run all the cells above, and we're up to here, 3.3, creating a training loop and training a model on batches of data. So that's going to be a little bit interesting. And
I need to create
yeah, this is a little bit behind the scenes.
chat
So
overlay for my
per batch
current
rather than
stream overlay. And that's that's a mouthful.
So let's hold myself to that note and make sure I let you know. So we'll go make another title here. Let's go creating a training loop and training a model on batches of data. So something a little bit different to what we may have seen before if we haven't created batches of data using data loader. And recall that just up above here, we've got something like 1800. There we go. So we split our data into batches rather than our model looking at 60,000 images of fashion and this data at one time. It's going to look at 1875 batches of 32, so 32 images at a time of the training data set, and 313 batches of 32 of the test data set. So let's go to training loop and train our first model. Woo-hoo. So I'm going to write out a few steps actually, because we have to do a little bit differently to what we've done before. So one, we want to loop through epochs, so a number of epochs, loop through training batches. And by the way, you might be able to hear some birds singing. The sun is about to rise. I hope you enjoy them as much as I do. So we're going to perform training steps, and we're going to calculate the train loss per batch. So this is going to be one of the differences between our previous training loops.
Look through epochs. Okay, there's an additional step here. Look through training patches, perform training steps, and per batch. Okay.
And this is going to, after number two, we're going to loop through.
So basically 2 for loops rather than 1.
Testing batches. So we'll train and evaluate our model at the same step or same loop, and we're going to perform testing steps, and then we're going to calculate the test loss per batch as well. Per batch. Wonderful. 4, we're going to, of course, print out what's happening. You may have seen the unofficial Pytorch optimization loop theme song, and we're going to time it all for fun, of course, because that's what our timing function is for. So let's get started. There's a fair few steps here, but nothing that we can't handle. And remember the motto, if in doubt, code it out. Or there's another one, if in doubt, run code, but we haven't written any code to run just yet. So we're going to import TQDM for a progress bar. If you haven't... I
think since this is a segment of its own, I'm gonna cut the stream short here. Yeah. It's better to start the segment as a whole tomorrow, isn't it? Now before I end, let's just view the unofficial Python and not Python Pytorch song. Unofficial Python optimization loop song.
Have visited. You see in loops like a Pytorch. If you we can never forget. So let's train. For an epoch in a range, Komodo.train, do the forward pass, calculate the loss, optimize a zero grad, loss backwards, optimize a step, step, step. Let's test. Komodo.eval with torch inference mode, do the forward pass, calculate the loss, print out what's happening. Let's do it again, again, again. For another epoch, Komodo.train, do the forward pass, calculate the loss, optimize a zero grad, loss backwards, optimize a step, step, step.
Oh, what's that? Okay, I think that's enough our song for now. By the way, this guy was invited to Harvard. Oh, you mean Daniel? Daniel, what's his full name? Daniel Bock, huh? He must be, is he a really prominent figure in the machine learning space then? Daniel Bock, YouTuber. Anyway, we live in a time where we get 25 hours of pure gold in for free. They have to get machine learning skills without doing a PhD. I guess he is prominent, isn't he? Brisbane, isn't that in Australia? There we go. Okay, anyhow, yeah, good educator, of course, yeah. I'm gonna call today for now. Really grateful of all the things we've learned today, and thank you, Akshunya, for being along with me. All right, okay, I'm gonna end the stream now. Yeah, I'll see you all in the next one. Take care, Ethel. I can't pronounce that. Take care till then. Bye.